Good morning, everyone. Uh, I'm glad to see all of you back after a nice, restful day yesterday. And we're starting our second part of the workshop. And our first speaker is Professor Andrea Klinkov.
Thank you. So, maybe I'll begin with a few general words. This is a school uh, dedicated to memory of Igor Krichever and somehow maybe seen a little bit as a continuation of the tradition he was starting. Um, so different speakers of the school, they talk about maybe different parts of their lecture related to different parts of Igor's work. It's my job to talk about his earliest work, which was in topology. So this is following Novikov Sergei Petrovich, who also very recently passed away. Igor did some very important work in topology, which will be the subject of my lectures, and then moved towards integrable system. But for him, I think that already in his topological papers, you see Baker-Archies functions and so forth. I think for him it was always the subjects were always very, very connected, and in fact maybe they foresaw the level of interaction. So right now there's if you look at the forefront of integrable system, there's lots of interaction between questions in topology and into geometry and so forth with integrable system. And this is maybe if you be more clear from Nekrasov's lectures. So this is, but anyhow, this is the subjects are really really interact very strongly. And so maybe this already in the Novikov school, they somehow foresaw this many years ago. And so my goal is to maybe report on just try to explain what's Krichever's elliptic genus and prove rigidity, other properties of this genus, and maybe say a little bit how this generalizes further toward what we do now in the field. As to why would people in integrable system be interested in this? So of course you can. It's of course great if you can apply your knowledge of representation theory, integrable system, and so forth to learn something about geometry. But maybe you will be, for those of you who don't know, maybe you'd be be important to learn that in fact there are many there's there's a ways to argue geometrically about formulas, and especially it's especially nice when you get to argue geometrically about formulas with elliptic functions, because if you have a complicated multivariate expression in theta functions, it's quite difficult to see that this is simplifies anyhow. Maybe it's equal to 0, and the typical kind of argument for proving various elliptic function identities is well, you check that this is an elliptic function, transforms correctly, and you also see the function, it transforms correctly if you shift by periods everywhere. But then if it's a rational expression, you'd like to show that it has no poles. And then traditionally people just do it by, they roll up their sleeves and they just kind of just do it to prove that all poles in some expression cancel. And geometry provides a much more powerful way to prove that something is some rational expression in maybe elliptic function, in fact, is regular. All poles cancel. In multivariate expression, that can be pretty complicated. And there's a geometric way to see that in fact they all cancel. And that's so if you're not interested in geometry, you still may be interested in this kind of arguments. Anyhow, now to the actual subject of my lectures. So I think maybe I'll put the notes somewhere for the time being, like here. So I think any discussion of, so this is about genuine. So any discussion of gender, I think it's a good idea to start it with maybe the most classical example, just the Gauss map. What's the Gauss map? So if I have, suppose I have an orientable surface of some genus, and it's embedded, for now, maybe it's embedded in R3. So maybe call it C, anticipating the fact that it's going to be an algebraic curve. And then to every point of this curve, I have the normal, since it's smooth. I have a normal direction, and I have the tangent plane. And so using either of these data, I can move it to a sphere, namely have a point with oriental normal mapped to the sphere with the unique point in the sphere with exact same oriented normal. Right, so this is this Gauss map. Maybe we'll denote it gamma. Okay. So if we were here, the sphere S2 will be maybe more canonically. What is the sphere? Sphere is the set of oriented lines in 3 space, so it's maybe Grassmannian oriented 1, 3 space, real. Or the same as oriented. So if I have an oriented line, then I have oriented perpendicular, so it's the oriented set of oriented planes, 2-dimensional planes in 3-dimensional space. So for every point here, we map to the corresponding point there. And if it's a map of surface to surface, then you can ask what's the degree of the map. So what's the degree of the map? If you look at any point here, you look at all of its pre-images and count them according to so there'll be some orientation. And if it's orientation, let's say they're all simple, then the orientation is preserved, you count +1. If the rotation is reversed, you count it -1, and that's called the degree of the map. And the basic fact of the degree of this Gauss map is 1 minus the genus. So this is where the word genus appears. So the genus, well, for the first time I write genus of 0, just genus. Okay? And so there are many, many, many different ways to prove it. And maybe one of them is if I draw my surface like this, and I look at the pre-images of the north and south pole. So it's like, if you look at the pre-images of the north and south pole on the surface, then of course they would be, so this would be the points on the surface where my tangent plane goes horizontal. So these are the critical points of this coordinate, maybe call it h, the height function. So these are the critical points, and then so this would be. And this critical points, this point will go to the north, this to the south, this to the north, this to the south, this to the north, and this to the south. And the orientation, whether the Gauss map preserves or reverses orientation, this has to do with the shape of the surface being either like this, or being a saddle. At the maximum or minimum, we get degree +1, and every saddle we get degree -1. So you get clearly, so there'll be, in this picture, it's clear that the degree would be 1 minus genus. But if the surface is embedded in any other way, that there's, again, the Morse theory will tell you that there may be more critical points, but since you can compute the cohomology of the surface using the critical points, the total number of those critical points, counting the index, would be 2 minus 2g. And since it's for north and south, so divide by 2, you get 1 minus g. Clear? So another proof is, so this is proof number 1. Another proof has to do with the fact that if I have, so if I have a vector field, so if I choose V, I choose V to be a vector field on the sphere. So it's a section of the tangent bundle, so section of the tangent bundle to the sphere. Then, so by the very construction, the tangent bundle here, so if I take the tangent bundle to my curve C, well, that's the pullback, right? Because you just have a space here, comes here, so the tangent bundle is the pullback of the tangent bundle to C. So if I pull back that vector field, it's a vector field on C. Sorry, C. Right? So if I have a vector field on the surface, I can count the sum over indices. So then I can take the index of this vector field V. Well, it's the sum over all points where this vector field vanish, the index of this vector field at that point. So if I have I'm on the surface, so if I have a point where the field vanishes, yeah. It's already almost in my mouth. I don't know. Is that better? Is that, I don't know. So this is, the vector field can, as I go around the zero, the vector field can make some number of rotations. And so here it rotates with the circle. So this would be index 1. And in this picture, it will rotate. Sorry. Like that. And this picture rotates opposite. Maybe this is a little too long. So this will have -1. And in general, this is what? This is self-intersection. So this is self-intersection of my whatever surface with surface. I'll write say self. See inside the tangent bundle. So if I what are these numbers? So if I have a surface, it's something two-dimensional, tangent bundle something four-dimensional. So if I have a two-dimensional, I can self-intersect it, and this would be, and if I count with orientation, this would be plus, this would be minus. And so in any case, Hopf-Index theorem says this is also called the Euler class of the tangent bundle, and Hopf-Index theorem says this is the Euler characteristic of C, right? But since again now when we pull back something by a map, this depends on the notion of the index depends whether I go around this circle counterclockwise, clockwise or counterclockwise. And so then the fact would be the fact that the index of the pullback, so this would be, so then I can sum over all points. I can sum over all points where this original vector field vanishes. For each one of them, I get the degree of the map, because that's what controls the intersection, times the index at my original point. And so this would be just, so this is a common factor, it goes out, so the degree map times the index of V, and so we conclude that the Euler characteristic of the surface, which is 2 minus 2g, equals the degree of the Gauss map times the Euler characteristic of a sphere, which is 2. And so this is a baby computation with characteristic classes. There is for a vector bundle, there's something called characteristic classes that we define at some generality in a second. But so the characteristic, if the bundle is pulled back, then the characteristic classes are pulled back. And the Euler class is an example of characteristic class. It says, so if I have it says how many times a section vanishes with multiplicity. So take Euler class of a bundle tells you how many times a section vanishes with multiplicity. If I pull it back, then I get the Euler class there times the degree of the map. And you can write if you, so we're not gonna, so the topological computations we're doing today, they all have analytic counterpart. And the analytic, and we're not gonna stress on this, but this is what people very often see in applications. Because, so this is, if the bundle is pulled back by map, then so you can pull back anything. We can pull back connection, we can pull back curvature, and so on and so forth. So on a sphere, so maybe application of that. So on a sphere, well, maybe it's too big. Well, I don't know. I drew it. Maybe I drew it too big. So the sphere itself, it's a homogeneous space. And in general, this will be very, very nice. We will always be pulling back for something which is homogeneous. So it's the rotation group divided by SO2. And you can use, there's an invariant metric on the sphere. You can, if since it's a metric invariant under a group, then in particular, parallel translates with respect to this metric was just given by the action of the group. So you can if you want to translate along a geodesic, then you just act by an element of the group that takes you along that geodesic. And so if I have if I have a geodesic triangle, and if I see how much, so if I start with a tangent vector, let's have a tangent vector here, translated here goes something like that, translated there goes something like that, translated back it returns by some angle, maybe call it angle theta, and the computation of how much it's going to rotate will just amount to the commutator commutation in this group, and this theta is just equal in fact, so this theta is equal to the area of the triangle. So in particular, so if I pull it back, so I have a metric, I have a connection, I can pull back all that data there. I get some connection with the curvature which is pulled back. And so then I get the property that if I integrate over my curve C, I integrate. So curvature, usually people say curvature is a number, but in fact curvature is a two form. It tells you by how much you rotate as you go around a small parallelepiped. So if I integrate the curvature of the tangent bundle to C, well, this is what? This is an integral which is just 1 minus G times the same thing, since it's a pullback by this degree of this map S2. And here is the curvature here is just the area. And so this is, right, so you get the property that this is, so the area of the sphere. I sometimes have to remind myself what's the area of the sphere. It is 4 pi. And so you get the Gauss-Bonnet. So in principle, many integrals, and that's especially true in sort of modern high energy physics. They're written as Riemannian integrals, or maybe even infinite dimensional integrals, but they have a meaning that they're characteristic classes of some vector bundles. So you can compute that integral by the rules of calculus, but you can also compute them topologically. That's in some sense. So we're not gonna dwell on any kind of connections and curvatures. In many books, characteristic classes are defined in this way, but we're not gonna stress that point of view at all. And so, but in fact, you can do better. Instead of, so there are two analytic sides to this story. You can do better. Instead of just doing just integrals, you can talk about. So there's there's a somehow slightly different analytic side of the story. One relates to the integrals, and this is what I'm trying to illustrate in this example. And another has to do with indices of differential operators, or maybe more generally pseudo-differential operators. Again, some things defined analytically, but in the end, it's some essentially integer. And so there is that side of the story here too. And so what does it maybe I'll use this board for 1 second. What does it mean that the degree, so what does it mean that the degree of the map is this? It means, so if I consider the graph of the map, so consider, schematically, consider the graph of the map. So this is my S2, and this is my curve C, and there's some kind of map, kind of graph of this map. Now on the sphere, what I can do is I can choose a point and then stretch everything away from this point towards some other point. Right, so for instance, on this, I can do like a Morse flow. Make everything go from the north to the south. Right? So what would be the result of that? If I keep doing this, I will get the result where I have my graph becomes a subset where this part is just collapsed to this whole, maybe I'll draw, this whole blue part is collapsed to this point, and the rest are the spheres which are mapped with degree plus or minus 1, the total number with counting with orientation 1 minus g. And so in other words, I have my Gauss map, so this is to say that the Gauss map gamma, you can commute to a map that goes like this. From C, you go to a wedge of the spheres, and then here you just, so wedge means, if I contract, so what's a wedge of things? When I join things at a marked point, so I collapse all this blue thing to a point, I get a wedge of spheres, and then this each individual summand goes with degree plus or minus 1, and the total number is 1 minus g. Okay. So if you're computing a Riemannian integral, something pulled back from here, that's good enough because you're if you somehow, you're not really worried about a point because computing an integral, so this has measure 0, so whatever lives over that point doesn't matter. So you just for a Riemannian integral, this argument is fine. If you're computing indices of differential operators, that's not really good because this is not a smooth thing, but you can smoothly. So there's a way to write a smooth cobordism between the. So I'll just explain. So there's in fact a smooth way to interpolate the Gauss between the Gauss map and the union of n1 minus g spheres. And how does this go? So imagine I look at the graph of a function. So I consider a function of x, which is maybe x1 square plus x2 square minus x square. And so, and what does the graph look like? So the 0, f of 0, this is, well, I can't really, it's hard for me to draw this whole thing. I'll just draw it. So at 0, I get a cone, which I'll draw just like that. And then for Minsky quadratic function, so this is going to look something like that. So I'll just draw a graph. Something like so. And so if it's for positive t, it will go something like that. for negative t, it'll go like so. I'm drawing the graph of this function. But since a graph of this function would require 4 dimensions, I'm skipping 1 dimension. So that says if I look at the f of f inverse of 1, this will look like, so if inverse is 1, maybe this looks like this. F inverse of -1, this looks like that. And f inverse of 0, this is a curve. Right? Everybody with me? So, which says that, so this means if I have a surface, I can in this way smoothly pinch any kind of handle on the surface, and in fact make a surface a bunch of spheres. In fact, they can make it nothing, because the surface in the 3 space is bound to 3 manifold, so you can it's cobordant to 0. But so the problem with just using this is an example of cobordism. This is some smooth manifold whose boundary, if I consider t to be between -1 and 1, the boundary is the value at -1 and the value at 1, and so that's a cobordism between this and that. The problem with just this particular cobordism in the context of the Gauss map is that it's not defined at the origin. At the Gauss map, at the origin, what's the Gauss map? The Gauss map here, the Gauss map of x, that is 1 over the norm of x times x1, x2 minus x3. And that's ill-defined at the origin, but we can fix it. We can put, subtract a small number times the norm of x, something like that. And so that will make what? This will make a hole, or make a picture like so. And then you think of a graph. What would the addition to this function do to the graph of a function? It will make a hole like that in the middle, and so this will lead to the fact that here I will get another sphere. And so now you see that smoothly, in fact, my Gauss map is cobordant really to cobordant. So this Gauss map is cobordant to the map you take the union, disjoint union of 1 minus g spheres. This means you take g minus 1 sphere and map it with the opposite orientation to the sphere. And so this is that makes sense? And so this makes sense that this has this kind of smooth interpolation. This has the advantage that it applies to indices of differential operators. So in particular, it says that if I compute the index, so of indices of elliptic operators in particular. So this is the sphere, the tangent bundle of the sphere has. You can give it a complex structure, and in particular, there'll be d-bar operator. So you can study the index of d-bar operator going from what? You're going from the functions to functions valued in anti-holomorphic forms. I write like dz. Okay. It's an elliptic operator. And so this would be, so this says the index of this operator so the index of this operator for the curve C, this would be 1 minus g times the index of this operator for S2. And so what is this index of this operator? That's the same. So you have an elliptic operator, it will have some solutions, some kernel with holomorphic functions, some co-kernel, which are this you can, so in this case, co-kernel, in fact, co-kernel, this function is really, so the kernel of this d bar, this is, these are holomorphic functions. On co-kernel of this d bar operator, that has to do with holomorphic differentials. And so that says not only this, some kind of Riemannian statements are, or you can compute topologically, but you can compute statements about indices of elliptic operators in this topological fashion. And so in these lectures, we will not deal with Riemannian integrals, and we will not deal with elliptic differential operators. Instead, when we see this, we say, well, that's just the Euler characteristic of the sheaf of holomorphic functions. So this is the, why is that? Is because if I take the sheaf of holomorphic functions, that this is the kernel. It's a, so C infinity functions. This is d bar z goes to 0. As a sheaf, this is surjective here with the kernel here. And so if you're computing the index of this operator, you might as well compute the usual Euler characteristic of the sheaf of holomorphic functions. And this you can tensor with any holomorphic bundle you want. And then this will compute the Euler characteristic of the sheaf of sections of this holomorphic bundle, the index of that operator. Z bar, yes. So we will not be, like I said, we will just in all situations when we have actual computations, we will have the manifold will be complex. This will be a sheaf of holomorphic functions, or sheaf of holomorphic sections of some vector bundle. This is a sheaf, and it has a usual Euler characteristic, namely the alternating sum of its sheaf cohomology. And this is, you will just compute that. But in principle, it computes, you can also phrase it as an index of a differential operator. And the hardest thing about this differential operator is to remember how to spell its name. I believe it's called like that, but it's maybe the hardest notion here. So okay, so now maybe to summarize to summarize this discussion, there's ways to they're interesting. Maybe what we're supposed to take from this discussion. There is very important notion in topology, the notion of a vector bundle. We'll get back to that in a second. This vector bundles, with vector bundles, you can associate, in particular, if you have a manifold that has a manifold by definition has a tangent bundle, very important bundle. And to bundle in general, in particular to the tangent bundle, you can associate characteristic classes, which are either they have to do with connections, or either have this cohomological flavor, and they have to do with connections, curvature, and so forth, but in the end can be computed purely topologically. Or you can maybe slightly more refined things that have to do with elliptic differential operators, and so forth, but in the end also can be computed topologically, just with a little more sophistication in topology. And this is the Khrushchev genus in elliptic things. So so there's cohomology, there's something called K-theory, which we'll discuss in a second, and there's something called elliptic cohomology. And Khrushchev genus is some elliptic function you associate to to a bundle on a manifold. And that again has some features, and which will be the subject of this lecture. Okay, so now. Right. So now a little bit more systematically. So suppose I have a tuple. Suppose X is as a nice topological space, some compact Hausdorff space. So this is so I'm not trained in general topology. I'm gonna stress any kind of general topology notions. All topological spaces we'll see in this lectures, they're all simplicial complexes or smooth manifolds or something like that. So this is, and so then, you associate to this a certain group, the K group of vector bundles, and what's a vector bundle? So to this you associate K of X, or also known as K0 of X. This is a ring. What's an element in this ring? So this is so first of all, what's a vector bundle? A vector bundle is also a topological space which projects to X, and the fibers are vector spaces. And so they will be interested in complex vector spaces because this is this is more interesting. So there's the notions of complex vector spaces. And the bundle is called, and we only consider locally trivial bundle. This means that if I look at the neighborhood of each point, there's some open neighborhood such that over this neighborhood, so a bundle may be called the bundle. So the total space of a bundle is called E. There is a map projection to X. And so if I look at the pre-image of this neighborhood U, this will have to be a product. And the transition functions, they're all transition. If I want to transition functions between different neighborhoods, they will have to be linear function in the fiber C. That makes sense? So such things, so if I have, maybe I should call this bundle V. My bundles will be typically called V. So if I have such object that I can consider, so given two bundles, I can do the following. I can form their direct sums. It's another bundle. Because this has to do with the fact that my transition functions lie in the group GLN. And so this has to do with the fact that if I have the group GLN1 cross GLN2, I can map it to the group GLN1 plus N2 and make transition function for a bundle just by stacking the matrices together. And this will be transition functions for a new bundle. And then I can also form a tensor product, which has to do with the fact that if I have, and this just corresponds to the fact that I can take, what this map? This is the maps of automorphisms of one vector space times automorphism of another vector space going to bigger vector space. That just corresponds to direct. So inside here, so maybe I should say. So when X is a point, then bundle is just a vector space. And so if I have some operation for a point, which is to say I can stack the vector space that forms direct sum, then I can, using the same operation, I can make it for a vector bundle and have the tensor product, similar for the tensor product of vector spaces. And these two operations, these two things make the set of isomorphism. The set of isomorphisms. Classes of vector bundles into a semi-ring. Semi-ring means where you can add and you can multiply, and this is distributive with respect to one another, but you cannot subtract. But you can introduce subtraction formally. So if I have formally, so define K of X. This is semi-ring. There's the semi-ring here. With subtraction formally added. So what does it mean added? It means just I can start with just an element be a sequence of, I can choose V1 minus V2, just a symbol. And I say, well, this is isomorphic. I equate this to some maybe W1 minus W2. Well, what does it mean they're equal? Well, that means that, so this means V1 plus V2, well, is actually equal to W1 plus V2. Make sense? Then, what? Right. I mean, we didn't introduce any other key, so this is for now KZ. And then you observe it's kind of a really basic fact and will be very, very important. Is that for any bundle, V, there exists an embedding into a trivial bundle. So, or put it differently, you can say any bundle V is a quotient of a trivial bundle. And this is maybe quotient is easier to explain. Is that, well, if I have a section is a map from the trivial bundle, a section of a bundle is a map from a trivial bundle to your bundle. And so if I have enough sections, if I have finitely many sections, which is assumed where the compactness is important, with finitely many sections, I can generate my whole bundle. So there'll be surjections or equivalently. We'll say this equivalently. There's a surjection from the trivial bundle. Easier. So if I have surjection, then going to the dual bundles, you can. The bundles also have dual bundles, and so if I have a surjection from trivial to your thing is the same as embedding for the dual bundle. So, and this is just find enough sections, and you can always, using partitions of unity, you can always find enough sections for any bundle. So this is, but then we're not doing algebraic geometry here. We're doing topology. In topology, so in algebraic geometry, things get really complicated. But in topology, things are very straightforward. If I have a quotient of a trivial bundle or sub-bundle of a trivial bundle, I can just take the perp using any metric I want on the bundle. So I'm not doing algebraic geometry, I'm just actual topological space of a sub-bundle. Then I can take the perp of that sub-bundle and have a bundle which is complementary. In other words, I have for any bundle, for any bundle B, I can write in the form. There exists in bundle A, there exists some number n, sufficiently large, such that V direct sum, the perp of V inside here, well, it's just a trivial bundle. So it's enough in this, when I want to subtract something, I might as well subtract. So I might as well assume that these are trivial, can be assumed to be trivial. Because if I, so this is to say that minus V equals minus Cn plus V. If I want to subtract, I might as well subtract the trivial bundle. And so in particular, in this relation, the relation that you identify, the bundles are equal in K-theory if they're stable isomorphic. Means you add a trivial bundle and they become isomorphic. It's a non-trivial relation. Like for instance, we're doing complex K-theory, but in real K-theory, if I take the tangent bundle of a sphere and add a trivial bundle, then this is trivial because the normal bundle to the sphere is trivial. The sphere is orientable. So if I take the tangent bundle plus the trivial bundle, I get the ambient R3 restricted to my sphere, so it's a trivial bundle. So this is a non-trivial relation. So two bundles are the same in K-theory if they become the same after adding some trivial bundles. So but more importantly, yeah, I guess you took my water. Is there some other bottle of water there somewhere in that? Oh. Yeah. So more importantly, in this construction lets you define analog. Remember we had this Gauss map. And this construction gives you an analog of the Gauss map. Namely, you say that, so if I have some bundle, so this is my space X, and I have some bundle V. So maybe I'll first draw a trivial bundle of some rank. And then I have my subbundle V, which is subbundle in the trivial bundle. Then I get a map to where? I get a map from at every point of X. This is just like the Gauss map. At every point of X, I can record which subspace in this fixed Cn corresponds to V. So I get the map to the Grassmannian of rank V-dimensional subspaces inside an n-dimensional space, the complex Grassmannian. Clear? And moreover, over this space, there is a tautological bundle. Whose fiber over a point. So what does correspond? this parameterizes, this thing parameterizes various, so inside of my Cn, this parameterizes subspaces of a given dimension. And so in particular, there is a bundle over that whose fiber is the space itself. Okay. That makes sense? And this is, so this is, maybe I'll write it as before it was a Gauss map. And my bundle V is the pullback. Sorry, V is the pullback of this tautological bundle. So we have all of the structures, all of the kind of structures that we had in this example of the Gauss map before, we can kind of develop in this situation. This Grassmannian is a very, very nice manifold. And it's a homogeneous space and so on and so forth, has a lot of geometry. And all of that we can transplant here. Or equivalently, we can think of trying to take, in some sense, what we would like to do is understand something about like a push forward of X under this map. In some cohomology, in homologic Bordism or something like that. This is equivalently. Either we're trying to pull back some data here and integrate over X, compute integrals or compute Euler characteristic, or we can try to say where this X itself pushes forward under this map. That makes sense? So why it's much better to take complex coefficients? It's because this Grassmannian, this cohomology, is much more interesting for complex Grassmannian. For real Grassmannian, you can study the cohomology of the real Grassmannian. This is also interesting, but it's all it's all Z mod 2 torsion, so it's not super interesting. For the complex Grassmannian, it's much more interesting. And moreover, since we're interested in things which are stably the same, so this is, we can think of what is supposed to happen is I'm free to increase n. I'm free to add trivial bundles to that. So I should really take a limit. So maybe we'll denote this rank by R. I should really think of a limit. So it means take a union over all. Take a union over all n of Grassmannian R n. See? So union of all the Grassmannians, increasing union of them. And this has the property that, in fact, the cohomology under this embedding, the cohomology extends very, very nicely. And so this Grassmannian, so you can say, if I embed, in other words, if I embed the Grassmannian inside the bigger Grassmannian, then the cohomology surjects. So this is so the map on the cohomology is surjective. And so the theory of characteristic classes so in cohomology, this is about the pullback under this map of the cohomology of this infinite Grassmannian, right? Grassmannian R infinity. And what is this cohomology? What does it look like? So let's start with R equals 1. And the Grassmannian of one dimensional. So this will be about character. So R is the rank. So for R equal 1, it's about bundles of dimension 1 called line bundles. So this is Grassmannian one-dimensional subspace inside n-dimensional space, and I drop C. That is the, just by definition, the projective space. And I'll also drop C here, so the projective space of dimension n-1. And this has a very nice cell decomposition. Composition, which you can, if you have never seen it, then you know, just one of the problems to do it. And again, the beauty of the complex case is that all the cells are complex cells. So there's all of even dimensions. There's no boundary maps between them. And so in the result, the cohomology of the projective space, this is generated by the class. So this is projective space. It has a space of dimension, open cell of dimension Cn minus 1, and has a complement, which is kind of the points at infinity. So this looks at the minus as a one-dimensional smaller projective space. So this is something of codimension 2, and it's so this is in terms of algebraic geometry, that's a hyperplane. You equate one of the linear coordinates. So there's the class Poincare dual to this hyperplane. So it's a codimension 2 class. It's this Poincare dual class. Maybe I'll denote it X. And then and that satisfies the relation. Well, if I intersect, so if I intersect X, if I intersect 2 hyperplanes, I get a linear space of codimension 2. If I intersect 3 hyperplanes, I get a linear space of codimension 3. And at some point, I run out of dimensions, so x to the n equals 0. Sorry, x to the, have my capital N and small n confused. So as n increases, so if n increases, that just becomes polynomials in boundary. If I take n larger and larger, I mod out by higher and higher powers of n, and in the end it's just this. And so what? Well, you're right. It depends on what you. Okay. You can. So with all these things, you always. Yeah. Okay. It depends how you mean. Right. You can take it. This is always the case whether you take. You know, this is like maybe when you open McDonald's book on symmetric function. In some sense, it's all about symmetric functions. The theory of characteristics of McDonald's book symmetric function. One of the first pages. It says, and when you define symmetric function, you take the inverse limit and the category of graded algebras, which means you only allow things of bounded degree. So that here you can, when you take a homology of such space, you can also consider where you take the inverse limit or inverse limit in the category of graded algebras. So I don't know. It doesn't subtract or add anything, so we can take series. No, I don't object. I mean, it's fine. It's a good thing. So okay. So then what? So then we take right. So what's another point of view on this? So this infinite projective space, which is after all the union. So one way to write it, it's the infinite linear space, which is just means the union of all finite dimensional spaces. And then you take out the origin, and you mod out by GL1. Right? Or equivalently, you can say This is infinite dimensional sphere where you mod out by U1. You take a vector of length 1. And so this object, infinite dimensional space or infinite dimensional sphere, is in fact contractible. So And so this is a contractible space on which the group acts freely and you mod out by the group. So this is by definition called as classifying space. And denote BU1. What does it? It's just why it's called classifying space. By this construction, every bundle, every line bundle is classified by a map to here. So which is called why it's so a map. A line bundle is the same. So in general, so if this is already in Pasha's lectures. If you have a vector bundle, it means you have some transition functions. It's equivalent to the corresponding principal group bundle. So a vector bundle of rank n is the same as principal GLN bundle. So or principal UN bundle. And so that's the line bundles are the same as principal U1 bundles, and they're classified by a map to this, and this is called classifying space. Now, in general, similarly, this Grassmannian R infinity, this is similarly, if you think about this like that, this is you take matrices. What's a Grassmannian? You take maybe first Grassmannian n. Grassmannian size n. What's that? So how can I parameterize an n-dimensional subspace? I can think of a map from an r-dimensional. So this is I look at the space of homomorphisms from an r-dimensional space into n-dimensional space. So I parameterize my subspace by coordinatized by choosing a basis in it. I look at the locus of maximal rank, and I mod out by GLR acting on the source. This is the fact that you take some open set and you mod out by the group. That's also expressed in algebraic geometry. It's a GIT quotient. This is stable locus, and you express it like so. In other words, this is the space of R, by n matrices of rank R, and then you mod out by GLR. And so then, of course, if you'd want this to make Grassmannian R infinity, well, it's the same thing, except you make this matrices infinite. And so if I look at the space of infinite matrices of rank R, that is a contractible space for the same reason as this space was contractible. And so this space, this Grassmannian, it's BUR. And so it classifies UR bundles, well, again, through this construction. And now, very generally, if you have just from general principle, if you have a homomorphisms of groups, this always induces a map between the classifying spaces. The same direction. And so what is this? To use this here, we're going to use the maximal torus, which is maybe I'll write it U1 to the power R mapping to UR. Take a maximal torus inside this group and go here. So this should give me a map from BU1 to the power R to BUR. And what is this map? The map is just, what is this map? It just splits this matrix into columns. So if I have finitely many vectors, I put them together, this may not have the maximal rank. There will be some locus where these vectors are linearly dependent. But I have an R tuple of non-zero vectors of infinite length. Then the locus where they're linearly dependent, that's infinite codimension. So this is, if I take, so this is to say there is a well-defined map like that. Because things, if I take R tuple of non-zero like vectors of infinite dimension, add them up, then this is up to infinite codimension, that's a well-defined map. And this induces a map in cohomology we think. And so this says to say that the cohomology, says that the cohomology of this BUR, this maps inside the cohomology of that space, which is the polynomials in our variables. And in fact, what is the image of this map? The fact it maps it isomorphically into the image, which is just symmetric polynomials. Because again, it's sort of like in Pasha's lecture when he was taking a G bundle, reducing to the maximal torus, and this is to say if I have a subspace, I can choose to write, if I have a bundle, I can choose to write it as a sum of line bundles, but that's up to an order. And so there is this symmetrization there. And so then the Chern classes abstractly correspond so abstractly the characteristic classes correspond to, I have for any symmetric polynomial, I want bundles of rank R, its characteristic classes, I take any symmetric polynomial, and that defines me some class in cohomology. So this is a class in cohomology where the degree of each variable is 2. Yeah. Make sense? So again, if you open McDonald's book, then you see that this is this algebra of symmetric polynomials is freely generated by elementary symmetric functions. These are symmetric functions. Elementary. And these are called corresponding. These are called Chern classes. What's the geometric meaning of Chern classes? The geometric meaning of Chern classes. So the meaning, I have geometric meaning, and then the following. That this is maybe first let's talk about let's talk about the top Chern class. So CR, which is, if I don't want to always remember where the what's the rank of the bundle, I will sometimes write C top. This is a class. This is a cohomology class of dimension 2R. So real defines some condition of codimension. So this is 2R is the real dimension. This is the real dimension of CR. And this is the locus where a section vanishes. Of, strictly speaking, the dual vanishes. So this is the dual, well, in real topology, in real topology, there is really no much difference between the dual space. I mean, up to orientation, up to constant conjugation is the same, but on algebraic geometry you can do this. So if I have a manifold of a bundle of some rank, I look at the section, generic section. This would be our equation. So it's something of defines me as something of codimension of complex codimension R, real codimension 2R. So it makes sense that this is a class in this cohomology. And how do we see this? Well, so this is all right. And I said, so to say what's the in my previous notation, that is supposed to be ER, and this is supposed to be the R symmetric function of x1 to xr. This is just product of n var x2 to xr. Right? And what if I look here, what does it mean the section vanishes? So if I look at this picture here, so this, any kind of statement like this, it's enough. So every bundle, so this is again the same principle at work. Every bundle is pulled back from the universal bundle. So it's enough to prove the statement for the universal bundle. What does it mean for universal bundle? For universal bundle, how do I get sections of the universal bundle? I have homomorphism from, so this is this quotient, this becomes the tautological bundle. So I have a homomorphism from the tautological bundle to the trivial bundle. So if I take any linear function here, I get a linear function on the tautological bundle. So I get a section of the dual tautological bundle. So what does it mean to take a linear function here? It means take any row of this matrix. If I take a row of this matrix, means I apply a linear function to this here. So I pick a row, and I want this row to vanish. What does it mean for row to vanish? Row to vanish, so remember we had our basis vectors, and we need all of them to have one coordinate vanish. Right? So this is a bunch of basis vectors. For each of them, one of them, there has to be the first coordinate, or any fifth coordinate has to vanish. That is a hyperplane condition on each of these basis vectors. So this is what it's. So this means each of these basis vectors has to lie in this hyperplane. So this is what this condition said. Right? That clear? So more generally, well, the fact that this is invariant, this is kind of clear because this map is equivalent with respect to permutation. That the fact that it has the line invariance, it's clear. The fact that it actually maps isomorphical to invariance, maybe you need to argue a little bit. Because here you just take a tuple of vectors and stack them together. It's obviously symmetric. Right? So this is whatever you're going to get as a pullback under this map have to be symmetric. You it's a little argument to prove that in fact this. All right. So now more generally, I claim that if I take C R minus I, this is the locus where maybe I have to look at my notes for this to get the indices right. So this is, I believe, this is where I minus, so I plus 1, right? Where I plus 1 sections are linearly zero. And this, how do we, this statement, in fact, immediately reduces to this statement by the following kind of reasoning. That this is supposed to be some general statement about all bundles, right? So somehow this is for all possible bundles is the statement. And so then in particular, it has to be the case when in particular we can take V to be of the form a trivial bundle of rank I plus some other bundle. And so a trivial bundle, from a trivial bundle of rank I, we can certainly make I basis vectors, and then not just a basis, and then one more, and then nowhere vanishing nothing. And so you only get, so this for bundles like this locus is the same as where the section of this bundle vanishes. So this locus, so this dependence condition is the locus where this section of this bundle. In other words, if I write a matrix, 1, 1, 1, 1, and then I ask for something, one more. So maybe I'll write it like that. So if I ask matrix 1, 1, 1, 1, and then something, and then it doesn't matter what here is. What's here doesn't matter. So when does this matrix drops rank? This matrix drops rank exactly where this vector is 0. And then the elementary symmetric functions have the property. So this is again. Yeah. Yeah, this is a locus. This is codimension. The complex codimension is R minus I. And this is somehow the codimensions work out correctly. And the elementary symmetric functions have the property that the metric symmetric function has the property that it's its unique symmetric function of a given degree. So maybe I'll ask for, say, E maybe E3 is the unique of x1, x2, x3, and so forth. This is the unique symmetric. This is maybe problem number 1 on the homework or something. This is the unique symmetric function of degree 3, such that if I leave 3 variables and pad everything by 0, then I get x1, x2, x3. It's a simple thing. It's an exercise. So that says the Chern classes of a trivial bundle are trivial, and so this padding by zeros corresponds to adding a trivial summand. And so then it means if you add something sufficiently trivial, ask for this kind of condition, you get the Euler class. Make sense? Now I have to see what else I was trying to say, right? And so okay, maybe to reiterate. But that was a good board. So maybe we can agree. So maybe I'll say it one more time. So if I have so what is again characteristic classes? So characteristic classes in cohomology so if I have characteristic classes associate a bundle V on some topological space X, and bundles will be always complex. In cohomology, this gives me this kind of Chern classes, C classes C, K, or V, which are the some kind of classifying maps gamma pullback of the corresponding EK. EK is in the cohomology of Grassmann. And then I can, for instance, I can multiply these classes so that they add to the dimension of my manifold, and I can integrate over X. So for instance, in our situation, with the Gauss map, there was a bundle of rank 1. It had first Chern class C1, which is the Euler class by this board. And so we were just looking at the Euler class. So the Euler class had degree in a computer. That's had to do with the degree of the Gauss map. So in K theory, you'd think that this is, maybe you should similarly study, well, what do you think you should do in K theory? In K theory, you think you should maybe similarly, study like K theory of that space and so forth. But in fact, that's unnecessary. K theory is in some sense like the best. In some sense, K theory is maybe the most concrete, in some sense, in my view, maybe the easiest of all cohomology theories. All you do is the analog of that is just the fact that you can take tensor operations of your bundle B. So with the bundle B, you have also tensor operations. So every tensor operation, you can have some tensor product of various exterior powers for bundle B. So this is the exterior. So you can have cup product. So this is some sort of analog of you take the cup product of CKI. And so while in cohomology, maybe you integrate over X the product of this CKI of V. These are some numbers you're going to get. Maybe in K theory, you compute the Euler characteristic of this bundles. So I have maybe a few minutes left. I don't feel like starting a new theme, but maybe I'll say a few words about where this is gonna go in the future. So in general, a cohomology theory is a contravariant functor from spaces to something, to some rings or abelian groups or something. That is to say, you have if spaces map one way, then cohomology, they pull back under map, they go the other way. And so, but to get interesting numbers out of topological computations, you're going the wrong way. You're trying to push forward. So this operations of integrating something along X or computing the Euler characteristic, they're examples of push forward in this theory. So that you have to define push forward is not abstractly defined. You have to define what it means to have a push forward, and we'll talk about it in due course. But this going the other way, this gives you interesting numbers. You not get so if you want to get a number, so you have so you have all topological spaces, and all topological spaces there is point. Of course, you can pick a point and map to the space and pull back something via this map. You're not going to be something very, very interesting. But if you go the other way, if you have a map to the topological space and map it to the point, then you have some notion of push forward under this map. That gives you some interesting global thing like that. And that, in this situation, it's a number, but in the situation when we're going to consider, there will be a group action. So there will be some group, some compact group G acting on X, and will also act compatibly on this bundle. In which case, these numbers will be not numbers, will be functions on a group. So this is how you get interesting functions from topology. You start with a wrong way map. You start with a wrong way map in push forward map in equivariant K-theory, equivariant cohomology, equivariant elliptic cohomology, and you end up with a function on a group. And then this is an interesting function. And so this is in this case it will be an actual. So if I have a group acting on the so this would be in the case of K-theory, this will be a representation. This will be for me the virtual representation. Of a group G. And so the trace in this representation would be a function on the group. And this would be a function on, this would be like a differential of that function, be a function in Lie algebra. And in elliptic cohomology, where this Krichev words belong, this would be a function like an elliptic function on the group. And the basic result about it is Krichev's theorem is a certain rigidity theorem. And what does that rigidity theorem says is that, well, there's in the end, it's like a Liouville theorem. There is no, if you want an actual elliptic function, then there's none, right? If you want actual non-singular elliptic function, there's none such. And so in some sense, this theorem is not particularly, the rigidity theorem is not particularly surprising if you can define that number topologically, because if you can define this number topological, that says you're going to get like an elliptic function in the group, and okay, there's no elliptic function, and so this would be a constant. Anyway, so that's. I think I have 1 minute left, but it's I think it's okay to end with it.
Okay, thank you. So we have 1 minute for questions. Any questions?
Right. So this, what was it for the? It's enough to prove it for universal bundle. For universal bundle, what is it? You have, you look at kind of infinite by R matrices, and what's in your row of this matrix is a section of the dual bundle. So if the row of this matrix is 0, that means this was an R tuple of vectors, means for every one of them, the first or whatever, first coordinate is 0. But the locus where the first coordinate is 0 for each vector, that's a hyperplane class. That's the corresponding x. So x1 is where for the first vector the first coordinate is 0, x2 is for the second vector the first coordinate is 0, and so forth. So that locus is really the product of hyperplane conditions. So that is x1, x2, xr. Yeah. Yeah. No. Any section. So this is. It's clear that it's rather clear that this is. If I take any section, any collection of section, that would be you can have any collection of section, any other collection of section. You can interpolate between them, and so that will be certainly define the same cohomology class. Yeah. Yeah.
The formula is a map from X to this one, from the like bundles. It's always a map from X to the point.
Say it again. Here? Well, point modulo group or something like that. Yeah. 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 In that sense, it's a map to the stack if you want. Say it again. No. Here it's C had to do. I had a complex vector bundle. So it's a map to n-dimensional r-dimensional subspaces of that fiber. Yeah. So it's just my fiber is C to the n, and this C to the n is this C. Yeah.
Okay, I think let's go for the coffee break because remember we have discussion exercise sessions.
Right.
Perfect opportunity to ask these questions.
Everybody knows that the problems are posted online. Yeah. Right? Okay, cool.
To be collected and graded by.
Yeah, team? Exactly. Yeah. So if there's no grade, but if you want to actively participate, it's encouraged. Yeah.
You were talking about
просьба заполнять доски слева направо. Это.
Хорошо.
Вот здесь видите, что показывает всем людям.
Понял. Так, что-то он не горит.
Все, слышно.
Заработало. Все, отлично. Чудеса науки. А я не вижу часов. Не вижу часов. Нет часов, да? Часов нет. Ну, просто чтобы как-то. Я понимаю, что счастливые часов не наблюдают. Вдруг кто-то будет несчастлив. Привет. Сейчас не закончится. Да. Окей, нормально. Нет, если я подожду. Закончить я должен в 12:30, да? Или...
Да, еще лучше, 12:29.
12:29.
Okay, so let us continue with the second talk of this morning session, and it would be by Professor Nikita Nekrasov, who will give a course on gauge theories and many-body systems.
So I'm done. Okay, so this is going to be a course on the relation between integrable systems, which I loosely call many-body systems because quantum and classical many-body systems would be probably main examples of this class of integrable systems, and the connections to classical and quantum gauge theories. So gauge theories are interesting for physicists because they describe most of the known interactions of elementary particles, and they're interesting mathematically because, among other things, in recent 40 years, lots of interesting ideas in topology, in particular, and in differential topology, came from thinking about solutions of equations, partial differential equations, which are motivated by gauge theory, and by studying the modular spaces of these solutions and studying homology theory, some intersection numbers and enumerative geometry of these modular spaces, and that led to the advances in understanding the invariance of four manifolds. Also, the related story concerns the invariance of knots and the categorification. So all these mathematical theories were motivated and kind of are developed in parallel with physics developments of gauge theories. Now, so I want to present this this relation in two ways, because I want to illustrate one of the ideas which is not that old, which is probably is in active development in the last 30 years, and that's the idea of duality. Again, I'm talking about the duality in the physics context. Of course, duality in mathematics is a very old notion and has lots of incarnations, from Fourier transform, from Legendre transform, all the way to Langland's duality. So one of the kind of simpler versions of Langland's duality is what I want to present. So namely, we will have two types of connections between these two subjects. So one would be the so-called direct, so to speak, direct relation of sort that gauge theory is equivalent to an integrable system. And so this is so this is kind of it's a rare situation when you can analyze the Lagrangian of gauge theory, maybe solve all the constraints represented in proper variables, and see with your naked eye that this is just the dynamics of some particle system, many body system. So this is interesting, but it's sometimes useful actually. We'll see examples of that. How is it useful? And another relation which is kind of indirect is that correlation functions of quantum gauge theory obey classical or maybe quantum equations of some integrable system. So what's the main difference between direct and indirect relation is the relation between the quantization parameters. So in the first case, the Planck constant of gauge theory is the same thing as the Planck constant of the integrable system. So you have literally equivalence of two systems, and so its equivalence is a classical level, and it persists as a result of quantization. In the second case, the quantization of one theory is not directly related to quantization of another. And so what plays the role of Planck constant is not so they have different meaning. And so this is why it's interesting, because you can maybe say something about the quantum system, quantum gauge theory by solving classical equations of motion of some integrable system, which is simpler, and maybe vice versa. So now, why is it interesting to physicists is that it could be sometimes this integrable system is the same on both blackboards, but gauge theories are different. And so this relation means that there is a duality between gauge theories. And that's what's interesting for physicists, because this relates simple questions on one gauge theory to complicated questions on another gauge theory and vice versa. So this is why it's beneficial to study that. All right. Now, this morning, when I just got off the plane, I got an email from Pasha Esingov, who told me that he already covered all the topics I was about to talk about in this in this lecture course. So, none of the ones he advertised. So I should probably do the same, right? But we have this saying in that repetition is a mother of knowledge. So maybe if I repeat, Pasha, that it will be. At least I'm sure that my notations will be different. So I apologize if you heard this before, and I'm sure you can read it in many textbooks. But all right. If what I'm talking about at the lecture is already known, then we can go over maybe examples which I'm sure Pasha didn't cover in the exercise session. Okay, so now my goal today is to give examples of integrable systems and give you a notion of Lax representation for some of them. And Lax representation, which we'll review, is sometimes the best hint that the integrable system has some connection to gauge theory. So this is the path to gauge theory. Okay. And so my favorite integral system is the Calogero Moser Sutherland Manibus system. So it describes particles which move in one dimensions, so one-dimensional so let's denote the coordinates x1, xn. They're indistinguishable. They are non-relativistic, meaning that so the Hamiltonian will be the sum of the kinetic term and so the kinetic term is quadratic in momenta. So I have coordinates x and momenta p, and so there is a symplectic form on the phase space of this system, which is the canonical. So I just give you the system and Darboux coordinates x and p. Now, what is the phase space of that system is a bit tricky. So let's start by, let's take r to the n without diagonals and take the cotangent bundle to it. And now I said that my particles are indistinguishable, so it means that the configuration space is not really the set of positions of my particles, but the set of modular permutations. But it's better to make the symmetric group act both on coordinates and momenta. And so we'll take the quotient of that by the action of symmetric group. And so the Hamiltonian, the classical Hamiltonian, has a parameter nu squared. And so there is a potential which describes the repulsion between the particles if nu squared is positive. So if nu is real. And so because of this repulsion, the configurations of finite energy don't allow particles to touch each other, to see the top of each other, and that's why I deleted the diagonals. Now, so this is so it's a Hamiltonian. We can write equations of motion. And remarkably, these equations can be packaged in the equation of Lax-Swann, with the where L is the so L is going to be an n by n Hermitian matrix with momenta sitting on the diagonal and nu times of diagonal. So so this is antisymmetric, but I multiplied by I and make it Hermitian. And so the claim is that there is a matrix A which depends on P and X, such that the time derivative of this operator, according to these equations, is actually a commutator of L with that matrix A. It's a good exercise, actually. It's not difficult to find it explicitly. Now, what it means that it implies that eigenvalues of L are constants of motion. Now, what are these eigenvalues? Well, if you imagine that, so your particles, since they repel, so they, when you wait sufficiently long time, they'll probably end up being very far from each other. And so in the limit when time goes to plus or minus infinity, up to some permutation. So the representatives of my particles will be very far apart, and so this off-diagonal term can be neglected. And so these eigenvalues are essentially the momenta, the asymptotic momenta. Plus minus stands for time going to plus or minus infinity. So the way how you order this momenta, it's depends on your, the way you do it, your accounting. You can order them according to the positions of particles. So the eigenvalues, of course, are defined up to a permutation. So the individual eigenvalues don't need to conserve. I mean, the individual eigenvalues at plus or minus infinity in time don't have to be equal. They can be permuted. But as a set, they are the same. So the eigenvalues are not very useful functions of P and X because they are solutions of some algebraic equations. You can form polynomial functions of momenta and rational functions of coordinates by taking the powers of the operator L and taking the trace. And so these will be also, these are integrals of motion. Now, I claim that this is the simplest example, maybe the simplest would be the free particles when nu is equal to 0, but it's one of the simplest examples of gauge theory. So let me explain that. So this is going to be the simplest example of a direct relation between gauge theory and integral system. So, what I'm going to review is known under different names. One of the names is the projection method of Alshanetsky and Perelon. And so in this method, one interprets the seemingly non-trivial motion of seemingly non-trivial evolution if I divide by k, then this Hamiltonian actually turns out to be H2. So the seemingly non-trivial evolution of the system is actually a projection of something very simple from a larger phase space. And so there is a large phase space hidden in this problem, which is the cotangent bundle. I mean, it's a vector space to the Lie algebra of group UN. So this is the Lie algebra times times the projective space of dimensionality n minus 1. Actually, we can do it even, we can make it even, let's do it even simpler. So, so let's just, for fun, consider the following simple symplectic manifold. It's just a vector space. It's a vector space of dimension. Sorry, what I meant here was Rn, of course. Later we will complexify certain things, so that's why I'm slightly confused here. Okay, so it's a vector space, symplectic vector space. Of dimension 2 because it's symplectic manifold, and then n squared plus n. Okay. So let's parameterize it somehow. Let's call the elements of the Lie algebra of UN. Let me call them I square root of minus 1x. So x will be an n by n Hermitian matrix, and the conjugate momenta I will call square root of minus 1p. So p is also Hermitian matrix. So these are n by n Hermitian matrices, and well, I have a vector. Let me call it vector v, and the covector w. So v is a vector, w is a covector. So that's my my space. And on this space, I want to study two things. So first, I want to introduce very, very simple dynamics. So the way I represent things, these are conjugate variables. So p is conjugate to x and w is conjugate to v. I hope it's clear. Conjugate in the sense of a symplectic form. Omega is trace dp dx plus dw dv, where I understand that you contract w with v as covector with vector, and here's a trace. Okay. And so let me define the Hamiltonian to be simply trace of p squared. So it's very simple Hamiltonian. And the time evolution it generates is that so at this point it's not clear why do I need this vector and covector. They just go for the right. Nothing is going on with them. So this part we can actually generalize. We can take any Casimir built out of P and consider simultaneously evolution with respect to different times. In principle, you can take k to be arbitrary, but the evolutions which will be generated by hk when k is greater than n can be reduced to the evolution which is already covered here. All right, so this is very simple. It's a trivial, just free motion, but in a large space. So matrix is just changing this way. Now I want to, the second ingredient which I want to introduce, and that's essentially what gauge symmetry is about. I want to say that my problem has a symmetry, and I want to perform the so-called symplectic quotient with respect to its symmetry. So symmetry. The symmetry will be generated by the group UN. And in order to see how it acts, well, so P, so G will send so let me combine my vector and covector. So into a complex vector. And so P, X, and Z go to X. So the only thing which Z does, it transforms under the action of the unitary group. So purists would have said that there is a little bit more structure which I used here, and so so T star of Rn was actually C to the n, and so that C to the n is the space with Hermitian structure, which is what my unitary group preserves. So that's the second I said that I'm talking about UN, it means that there is a space with a Hermitian structure. So that's T star to the n. Right. Okay, so it's a symmetry, and it's a symmetry which preserves the symplectic form, and which is an exercise, by the way, and of course it commutes, it preserves my Hamiltonians, and so it means that if I take a simple motion in my large phase space, so this is large phase space. So here I have a basically straight line motion, but then I have the action of the group. So these are G orbits. So the small phase space didn't denote it, so let's call it. So this is P large. And this is P small, which is P large symplectic quotient with respect to G. I will in a second remind you what it means. So on the small phase space, this trivial motion may now look complicated because I'm performing identifications with respect to the group action. You all know this. This is what you experience when you try to stand on rotating table. So, in other words, I mean, the simplest example of this construction when n equals to 2, we can actually discuss. So just take a free motion of a particle in the three-dimensional space. So R3 is essentially, it's a Lie algebra of SU2. So we remove center of mass. And then, so this is a free motion, R. And then try to project it onto the quotient of R3 by the action of the group of rotations. So it means that your invariant is the radius, the distance from the origin. So now, if you look at the time dependence of this object, well, it looks like, so if time goes by, this is R, which is strictly positive, well, it will have some shape. So it looks like now the particle which is represented by the radial coordinate of my free particle in 3 dimensions experiences some force which repels it from the origin. So that's the centripetal force which you, yes. Yes, yes. So we'll get there. So you see, in the ordinary world of spaces with symmetry, the normal thing to do is to take a quotient. So you just take equivalence class. You go from the space to the equivalence classes, where you just contract the whole orbit to a point. But we are now in the world of classical mechanics, where we deal with symplectic spaces, symplectic manifolds, and if you just take a quotient of a symplectic manifold by the action of the group, the quotient is not a symplectic manifold. So there is a procedure which remedies that, and so let's review this procedure. So there is something called the moment map. In fact, I recently checked, because Pasha Wigman, who is probably here, was telling me that it should be momentum map, and I was arguing with him, and then it turns out that he was correct. So in English, it should be called a momentum map. It was moment in French, because in French the momentum is impulsion, just like in Russian. So but somehow in translating between languages, things got confused. So the moment comes from angular momentum, and so it should be momentum map. And so this map is the map from this large phase space to the space dual to the Lie algebra of the group, which acts on this space, which acts by preserving symplectic form. And so what this map is, it's sort of a collection of all Hamiltonians which generate the symmetry in question. And so let's compute, instead of explaining what it is in general, let's just compute it. Let's just compute it in this example. Maybe I can remind you first what it is in this example of a particle moving in three-dimensional space. So the particle moving in three-dimensional space has the six-dimensional space as a phase space. So there are coordinates and momenta. So these are the. And the symmetry in question is the group SO3, which rotates P and R. And what are the generators of that symmetry? Well, these are, in this case, precisely the angular momentum components. And that's the example of the moment map. So this is the map from the six-dimensional space to the three-dimensional space, which is dual to the Lie algebra of SO3. So this is an example of momentum map. So what it is here, so we need to, first of all, compute the infinitesimal version of the symmetry transformation, and then ask what generates these transformations. And then, so if I take G to be close to identity, so psi is now in the Lie algebra of UN, then the kind of a vector field which corresponds to this element of the Lie algebra psi, evaluated it, is well, it's just the commutator of P with psi, commutator of X with psi, and it's minus psi. Let's see. So I said that this vector field preserves the symplectic form, so it has to come from some Hamiltonian. So there is a Hamiltonian which generates this vector field, and the vector field is linear in psi, so the Hamiltonian will also be linear in psi. And So this will be the part which generates these transformations. So what I mean is that by that is that if I differentiate h with respect to x, I should get minus this quantity, and if I differentiate with respect to p, I should get this quantity. So if I didn't make a mistake, that's what I should get. And then this part is generated by a rank 1 matrix Z tensor Z dagger. So if Z is a vector with components Z1, Zn, this matrix is has components Zi times Zj bar, Ij from 1 to n. So this guy is linear in psi. Therefore, it comes from some. So it means that it's a pairing of some covector on the Lie algebra, which depends maybe in a nonlinear way on p, x, and z with psi. And so this part is the moment map. This is mu p, x, and z. So mu now, there is one important correction, which is that this map, of course, this map is defined not uniquely because the Hamiltonian. So the relation between the vector field and the Hamiltonian is not one-to-one. So the vector field associated with the Hamiltonian is the derivative. This differential of the function, the derivative of the Hamiltonian, to which we apply the inverse of the symplectic form, the Poisson bivector. I don't know how you want to put it. I'll just apply. So now you see there is a derivative here. So if h, if my h and your h differ by constant, we'll get the same vector field. But if I know the vector field and I want to reconstruct the h, I can only do it up to a constant. So, so this definition that will reconstruct mu of psi up to a constant, which is linear in psi. And in general, so there is a little bit of cohomology problem. Whether one can adjust these constants in a nice way. A nice way is where the Poisson brackets of the moments evaluated at different elements of the Lie algebra agree with the moment evaluated on the commutator. So this is the equivariance, G equivariance of moment map, which is usually required, and so that restricts the freedom in choosing the constants, but still leaves some room for this constant if your group is not simple, particularly if it contains a center. And so here, in this precisely, in our case, UN contains a center, and this center allows me to add a constant, which I will call mu, times the unit matrix. Is there a question? Okay, okay. I was hoping that you will point a mistake because I already tricked you. I mean, I made a mistake just so. Well, this is Hermitian. This is anti-Hermitian. So there is an I somewhere missing. Now, this vector product of P with R in the three-dimensional case is the commutator of two 3 by 3 antisymmetric matrices expressed as a vector. So this. Okay, so now we almost ready to project. So what do we project? So this symplectic quotient, we take the preimage of 0 of the moment map. And because of the equivariance, so this is why I made this speech about equivariance, this is a G invariant submanifold. And so we divide it by G. And they claim it that this is symplectic. This is symplectic. Well, it's a manifold if the 0 is a regular value of moment map, which is the case when nu is non-zero and positive. So the projection. So now we can discuss what's going on with projection. So let's solve the equation. So let's solve the equation u equals to 0. In other words, P commutator x is equal to square root of -1 nu times unit matrix minus z times z dagger modulo G symmetry. So modular these transformations. Well, since P and X are Hermitian matrices and my G acts by conjugating, I can find the representative in the G orbit of the triple PXZ where X is diagonal, for example. So there is a representative. So let's fix that representative. It still leaves us with a little bit of symmetry because there are still transformations of this form which preserve the fact that X is diagonal. And so this reduces G to the product of U1 to the N, so diagonal matrices. And there are also permutations. So there are transformations which will permute the eigenvalues of X. So we'll deal with them later. Now let's solve the this equation. In this basis, when X is diagonal, let's look at the, well, we can just write this matrix now. P X ij is P ij times Xi minus 6j. And this matrix, so this should be equal to square root of -1 nu delta ij minus zi zj power. Now, if I equals to j, the left-hand side vanishes. Therefore, nu should be equal to absolute value of zi squared for any I. So now our vector z has entries which all have equal absolute value, square root of nu. So I'm assuming that nu is positive. It's obvious, like if you take the trace of left and right hand side, that this the that if nu is negative, then you have no solutions of this equation. So nu is positive. Now I'm using those remaining transformations, which so G of the form so G, which is just the diagonal matrix of phases, which allows me to make Z to be square root of nu, so make them all real positive. So that now reduces. So that reduces the group of remaining transformations, reduces them to just permutations, because they will not change this vector Z. They will not change the fact that X is diagonal, but they will still act. We will permute eigenvalues and we'll do something with P. But now we can solve for P. So P from this equation. So when I equals to J, the diagonal part of P is not defined, is not determined because it's multiplied by 0. So P can have an arbitrary diagonal part. And for when I is not equal to J, then just divide the right-hand side by xi minus xj, and we'll get the solution. So square root of -1 nu delta ij minus 1 xi minus xj. So maybe I erased the formula, so it's okay. So maybe I made a sign mistake. Okay, so what's the conclusion? The conclusion is that now, if I parameterize my space of conjugacy classes, if I parameterize the orbits of the group action by diagonal x, or by eigenvalues of x, if you like, in this basis when x is diagonal, P has this form, and now the motion looks non-trivial, because now so x1 of t, xn of t are eigenvalues of x1, so this diagonal matrix xi of 0 delta j plus, let's say I do only the flow for the quadratic Hamiltonian, and so then this is pi so well, it looks non-trivial. So now we I mean, if even that is not exact. So I'm not sure what I'm trying to say. So what looked simple, once again, so what looked simple x goes to x plus t p, p goes to p. Now it's complicated because now I keep performing the compensating transformation. So now I accompany my simple motion with transformation G, which depends on T, in such a way that this matrix is diagonal all the time. And so now it looks like a very non-trivial dynamics. Now, where is the gauge theory and gauge symmetry? Well, this is the gauge symmetry. So this is gauge transformation. So it's a symmetry transformation which depends on time. And the way to represent it by Lagrangian, from which we will derive these transformations by variational principle, is to start with the usual Lagrangian associated with the symplectic structure and the Hamiltonian. So dot means derivative with respect to time. And then I can write similarly z dagger, z dot minus trace p squared. Plus, so if I stopped here, that would be just a Lagrangian describing the free motion which we discussed before. So here, the gauge symmetry is not implemented. It's here, this Lagrangian describes the system which has a symmetry, but that symmetry maps one solution to another solution. If I want to declare the symmetry as a gauge symmetry, so I want to reduce the number of degrees of freedom, I introduce Lagrange multiplier, and it is traditionally denoted as A sub t times mu. So, trace. In fact, more canonically, I could have written this as mu times A sub t. So A sub t, it's a new field, new variable if you like. It's actually one form valued in the Lie algebra. It's one form on time, so on t. T is my parameter on its time. So it's one form in time direction, and right. So A sub t is the one form valued in the Lie algebra of G, and mu, remember, was the map from the phase space to the dual space of the Lie algebra. So they pair naturally. So it's mu of actually right, mu of p x z evaluated on A sub t. Now there's a little bit of adding oranges and apples here, because so this term is naturally, it's a one form on time. So you can write it as p dx. And so this is also one form. And the only term which requires, which actually depends on parameterization of the trajectory is Hamiltonian. So we put dt here. And instead of writing Lagrangian, we will write an action. So the point is that now, if I take this functional on the space of time-dependent fields, so p depends on time, x depends on time, z dagger all depend on time. So S is a functional on maps of R, or maybe an interval valued in a large phase space, times one forms on R valued in the Lie algebra of my gauge group. But now, oh miracle, this functional actually has a symmetry. And so we can actually divide it by the action of the group of maps R to group. And what is the symmetry? Well, it's a symmetry which I wrote here. So it acts on the variables p, x, z in this way. But now, so if this is now a trajectory. So G is also, so G is now allowed to depend on time. So, so if you take this action and perform this transformation, you will find that it is not invariant under these transformations. It is only invariant under transformations when G is time independent, it's constant. However, the point of adding this term is to make the whole thing invariant, provided now that A sub t transforms. In this way. And so this is the first glimpse of gauge invariance. So A sub t is actually a connection on the trivial G bundle over the line, the timeline. So, so this many-body system is actually the simplest one-dimensional gauge theory. It's a gauge theory whose space-time is just time. There is no space, but the variables have the original variables have some metric structure, and so that it's sort of the hint that maybe you see A sub t. So it is valued in the Lie algebra of the unitary group. So it's one form of these are just n by n matrices, like n by n Hermitian matrices or anti-Hermitian matrices, and so are P and X. So it sort of suggests that maybe in a better world, P and X, or maybe both P and X, also become the components of some gauge field. Maybe now it will be the gauge field on a higher dimensional space, and then that would mean that this system has some generalization or deformation in which these extra dimensions will be visible. And so that suggests that one should study not just one should study deformations, maybe integral deformations of this Calogero-Moser system. When I say this Calogero-Moser system, I mean the rational Calogero-Moser system, because this potential is given by a rational function. And indeed, so okay, so just write it down. So maybe P and or X are also one forms, also components of a gauge field, of a connection. So we have time. So this is A sub t. That's Lagrange multiplier for the moment map. And maybe there are additional space directions, so that maybe A sub x is going to be x, and A sub y is going to be p. And so that would suggest that the Calogero-Moser system, rational Calogero-Moser system, has deformations, maybe integral deformations. Well, the answer is yes. So all these scenarios are realized, and they correspond to a plethora of generalizations and deformations of this model, which we'll encounter. So 3 generalizations. So there is rational Caligari-Moser, and there is trigonometric Caligari-Moser, also known as Sutherland. And then there is relativistic. Actually, there are 4 generalizations. And there is elliptic. Relativistic rational, known as rational Roisenars. Schneider, trigonometric Reisner-Schneider, and then there is actually elliptic Reisner-Schneider. And I'm out of space, and it's a good thing because below are conjectures and still unexplored territory. But these arrows, they correspond to actually uncovering additional dimensions of space. And so these models correspond to different gauge theories living in different space-time dimensions. So this thing corresponds to 2-dimensional Yang-Mills theory. This thing corresponds to 3-dimensional Chern-Simons theory. This is some kind of hybrid topological holomorphic 2D Yang-Mills theory. And this is a so-called 4-dimensional hybrid topological holomorphic Chern-Simons theory. Okay, so these are words. What do I mean by them? And, where do we go from here? So let me explain maybe. Let me explain something simple. So trigonometric Caligari-Moser Sutherland. This is the system where your particles now live on a circle. So R becomes R mod Z. So we replace the rational function for some reason, it's better to write it this way. So, okay. So you can think of this as of the system where the symmetric group, which was permuting particles, got promoted to affine Weyl group. So in addition to permutations, you also have shifts by the period. So the period being 2 pi. Yes, 2 pi. So 2 pi z. Yes.
Are talking about functions of particles, symmetries, and affine Weyl groups. So certainly you should get lots of representations of Ray groups, Coxeter groups, and many similar groups, right?
Yes. I mean, the verb should has kind of a kind of too much of imperative for this time of the day. I mean, I haven't even I didn't even start talking about representation theory, which is behind this story, because you see, this is, for the moment, is classical mechanics. So representation theory usually is associated with quantum systems. So in quantum systems, we would promote maybe P to an operator of d by dx, and we will be looking for the eigenfunctions of the corresponding operator. Yes. Yes. It was not, right. So where was it? Oh, sorry. Okay, so this is, just look at this term, p dx. So d means time derivative. So if you apply the transformation I mean, students should do it at exercise session. So if g depends on time, so dx on g, and so we will get a correction term. And this correction term will be precisely mu, like commutator p with x. And so that's why you need the inhomogeneous part. So that's kind of the simplest way in classical mechanics to understand where the origin of the long transformation property of gauge fields, of connections. They're not just one forms, they're connections. All right, so yes, so there is an old construction of Kazhdan, Kostin, and Sternberg, which explains how to get this system by a projection method. In their construction, you replace the Lie algebra of UN in this large phase space by the group, and repeat the whole story. This is not the way to see the emergence of additional dimensions. In order to see additional dimensions, you promote everything to loop space. So promote UN to loop algebra of UN, or precisely to the central extension of the loop algebra. So these are now functions of an additional variable. Let me call it x. So x belongs to a circle. This is different font. This is not that x. And so these are, okay, so this is, so E of x lives in the Lie algebra, and C is just a number. And so it's so there is a structure of Lie algebra on the space. So you take a pointwise commutator of Lie algebra valued functions. So that would be just what's called a loop algebra. Sorry, this is. And then, but the center. So the C1, C2 they disappear from the commutator, but something appears instead. And that's the integral over the circle trace U1 DE true. So again, a very useful exercise for students is to check that this formula satisfies Jacobi identity. And so now the dual space actually consists of interesting bits. So there are so EXC, and the vector space, which is dual to the Lie algebra of the Cosmodi algebra of the current algebra, is actually the space of differential operators of first order, sometimes called lambda connections, but physicists call it K connections because there is a K, where K and C are real numbers. So E and AX are G-valued functions on S1. And the reason I wrote I combined A sub x and k into the first order differential operator is that you verify that the coadjoint action, so the action on, so A sub x pairs with E. So the pairing is integral over S1 trace E A sub x dx plus kc. So the claim is that if you act on the Lie algebra by the Lie algebra in the adjoint representation and compute the coadjoint action so that the pairing is preserved, then this coadjoint action will act on A as on the differential operator. And so when you integrate it to the at the level of the group, the loop group action on this quadruple is so it's pointwise conjugation of E and gauge transformation of A. So K is invariant, and C actually transforms in a way which I will not write. But it's computable. It's not a big deal. So so from that, we should think of this E is an analog of P, and X and A sub X is an analog of X. So now the commutator P of X gets promoted to the covariant derivative of E. So there is one step here which is not very motivated, but I will just do it. K is kind of an inconstant of motion, so I will fix it to be 1 once and for all. And so then the commutator will become just a covariant derivative of E, which is the derivative plus the commutator. Now, what happens to this term ZZ dagger, or nu times 1 minus ZZ dagger? This is part of what, sorry? So this is the moment map for the action of the group on the cotangent bundle to the Lie algebra. So this is the moment map. So mu was that. So this is the part of mu which came from T star of the Lie algebra, and now the same part becomes that. So the new term is the derivative acting on E. Now, this strange notation is that in physics, this is called electric field. That's why it's called E. And this is called, vector potential. And this particular combination, so this derivative, the covariant derivative of electric field, is sometimes called the Gauss law. This is Gauss law in one space dimension, so it's maybe not that recognizable. We normally discuss Gauss law in 3 dimensions, and we measure it by the number of flux lines, force lines of electric field piercing some surface. So we measure it by divergence of the electric field. So this is the one-dimensional divergence of electric field in a non-abelian case. Now this term comes from, remember, we had this copy, this n-dimensional representation of the unitary group, which we used for one thing. The use of that was when we went to the gauge, when we found the representative where diagonal representative of x, so fixing the gauge when x was diagonal did not completely use all the symmetry we had. So there was a little bit of symmetry left, and that was of diagonal transformations. And so we needed this vector in Cn to absorb this remaining symmetry. So something similar happens now in this infinite dimensional case. So the analog of x being diagonal is now a sub x is diagonal and constant. So these are constant respect to x. Let me say a few words about this representation. This is known as Flaquet-Lyapunov theory. So the question is, if you have a function, if you have a matrix valued function, so n by n matrix valued function on circle, so a sub x, and I studied up to transformations of this form when G is a map, it's a periodic function, periodic group valued function. So what is the normal form? I mean, to which form can I bring this function a sub x? So what is the canonical normal form? And so I claim that you can make a sub x diagonal and constant. So all the all the x dependence can be absorbed in G. And so this is Lakelian-Punnov theory. Well, basically, you try to solve the equation. So you try to make A 0. So you try to make A vanish completely by this transformation. Well, that would require solving an equation A equals dGg inverse. I mean, I want to kill A. That means that find G such that A can be written in this form, right? Because Lie algebra valued, yes, Lie algebra valued. Well, n by n matrix. It's a Hermitian matrix. Just divide by I. Anti-Hermitian matrix. Anti. Okay, well, how to solve this equation? Well, just means that I need to solve the equation dxg equals ax times g. So it's a first order ordinary differential equation. You give yourself some initial condition, then you just solve. What's the problem? The problem is that by the time you come back, you are in a circle. So you start with g, let's say it's 0. You can choose anything you want, and then you solve. So g of x will be path-ordered exponential. Sorry, path-ordered exponential from 0 to x integral a sub x. So this notation means Dyson series. So it's 1 plus the integral plus order plus iterated integral. So by the time you came back, you need not arrive at the same g you started with. And so that's the abstraction to finding such g. So the abstraction to kill A is holonomy, monodromy. So it's path of exponential. So this is some, so if I start at point 0, so it's some group element which has eigenvalues. And so the eigenvalues of G, essentially the logarithms of eigenvalues of G is what enters here. So the e to the 2 pi I x1 actually maybe okay, so if 2 pi's are there, then there's no 2 pi here, and there is 2 pi here. So sine squared pi xi minus xj. Okay, so you can find G such that so you cannot find G such that dg will be equal to A times G, but you can always find G such that dg equals A times G minus G times the constant diagonal matrix. So that way you will undo this holonomy. So okay, 3 minutes left. Right. So so if I find the gauge, so if I make a representative for A to be constant diagonal, there are still transformations. There are still transformations of this form which will preserve the fact that A is diagonal, but they will change the eigenvalues. So if you take now the G of the form e to the 2 pi I and 1, sorry, I 1x So remember, x changes between 0 and 2 pi, and my g should be periodic. So that forces numbers n to be integers. And so that will shift. So such transformation applied to A, which is diagonal, will shift xi by an integer. So this is the affinization of the Weyl group, which I was talking about. And so it okay. Now if you, sorry, yes, I forgot. So I needed to explain this thing. So these are transformations which change eigenvalues, but there are also transformations, so G of the form when theta is a constant. So these transformations will not change A at all. And so we need the analog of the Z vector to absorb this remaining symmetry coming from those vectors. And we need just finite dimensional, just one vector space C to the n. We don't need fields. We don't need x-dependent functions varied in C to the n. And so that's why, in the end, it turns out that the contribution of this, so the analog, the loop analog of this momentum, this term in the moment map becomes delta function times nu times 1 minus z dagger. So now I've said everything. So if you combine this plus that, set it to 0, solve the moment map equations, and then compute the Hamiltonian, which is the integral of the quadratic Casimir applied to the electric field, you will get that Hamiltonian of Sutherland. So this is how, so in a few examples, I showed how one can see directly how gauge theory, simple gauge theory, is actually equivalent to a classical mechanical system of interacting particles. So next we'll discuss various ramifications of this story. We'll go from two-dimensional Yang-Mills theory living on smooth manifolds, maybe on cylinders or on pairs of pants. We'll generalize this story to Yang-Mills theory on foams. And we'll get lots of integrable systems. I don't know what the spine of any manifold is. So I'll explain what I mean by foam. Maybe, again, maybe it's not what other people knew. I actually, sorry, foam is something, it's a word that somebody put in my mouth. I call them origamis, actually. So these are spaces with corners, junctions, and all kinds of similarities. Okay, my time is up. So see you all in the afternoon.
Any questions?
Yes.
My question is it possible to write just this action and now start from the general question of the production and obtain this?
Okay, so maybe the impression that it was heuristic was because I was doing it in a, I mean, this is completely rigorous. It's well, it's what can I say? So there are two ways of thinking about it. So one way is just straightforward generalization of an analysis from fine-dimensional Lie algebra to Kac-Moody algebra. And another way starts by saying that let's take the standard action of Yang-Mills theory, which I didn't introduce, write it in the canonical formalism, so write it as a pass from Lagrangian to Hamiltonian. Yang-Mills theory in the presence of sources. So there's an element here which corresponds to this delta function. It means that you have what's called the Wilson line in some representation. So this is the straightforward analysis of the Gauss law in two-dimensional Yang-Mills theory in the presence of a single Wilson line. And so tomorrow I plan to discuss what happens when you have several Wilson lines and maybe junctions and more general things. Now, the secret of this is, of course, that in two dimensions, Yang-Mills theory has no propagating degrees of freedom. So it is not very surprising that what is called two-dimensional gauge theory is actually equivalent to something which is actually one-dimensional. One-dimensional meaning it's just this, classical mechanical system. There is time and there is no space as such. These degrees of freedom, these coordinates of these particles, are precisely the eigenvalues of the holonomy of the dynamical gauge field around the circle. And so these other examples which I mentioned in this table are similar in that way. So these are all theories which have essentially no local degrees of freedom, but they have global degrees of freedom. So depending on what space-time manifold you put them, you will get quite non-trivial mechanical system, classical mechanical, quantum mechanical system, depending on whether you study classical theory or quantum. In the last three lectures, we will be discussing much more sophisticated relations between integrable systems and gauge theories, where the theories will actually live on high-dimensional spacetimes. They will have local degrees of freedom, but there will be an additional structure. There will be a nilpotent operator acting in the space of states of the theory, and the cohomology of this operator will turn out to be the space of states of something finite dimensional. And so that's this indirect relation.
Okay. More questions?
Yes. Yes, they will appear in Lagrangian, but they will only live at the point x equals to 0. So the variables z and z dagger live only on this blue line. So they continue living in time, but they don't live in space. They live at one point in space. So Wilson line. So Wilson line represents if you imagine a very heavy charged particle, so heavy quark, like top quark is very heavy, you can actually make it follow classical trajectory as opposed to light particles, light quarks, which are all over. You cannot squeeze them you cannot pinpoint them at that point in space. But heavy objects can be localized in space, and so that's what this represents. Of course, there is a bigger, better world where we sum over all Wilson lines. So we have and make them dynamical. So that's that's why I will consider, more general situations when they have a dynamics of their own. And so then the sum over all lines can be represented by another field. So that would be now in non-trivial theory, two-dimensional QCD, for example. So Young-Mills plus charged matter. So that theory in itself is not solvable, but if you expand it in the number of particles in each sector, it can be approximated at least by an integrable system, which is of that kind or some generalization.
Okay, I think we should probably thank Nikita again and take a lunch break. There will be opportunities to ask more questions during coffee breaks, during discussion sessions, etc., etc. Okay.
Он говорит про Потом проводить манипуляции. Давайте сделаем так.
Okay, let's start our afternoon session. The first speaker is Sergey Landau, weight system related to Lie algebra.
Thank you, Sasha. First of all, let me show a list of papers related to the subject I'm going to talk about right now. This is not a complete list. And several people are involved in this research, mainly my students, Joki Young, who is present here now, who is now a member of BIMSA, Polina Zakorka, who is also here, Polina Filipova, now Polina Zinova, and Nadia Kadaneva, as well as Maxim Kazaryan, who is an ideological, probably, leader of the group. And what this is all about. This is related to study of knot invariance in the framework of Vasilyev's theory of finite type knot invariance. In Vasilyev's theory, any knot invariant taking values in a commutative ring can be extended to singular knots. We start with smooth knots in the 3 space, and according to Vasilyev's scaling relation, we extend the invariant to singular knots, and a knot invariant is said to be of order at most n if its extension to singular knots with more than n double points vanishes completely. To such an invariant,
one can associate a function on chord diagrams. Chord diagrams are very simple combinatorial object consisting of the circle, which is the Wilson loop from Nikita's talk. The circle endowed with several chords and chords in our case, having pairwise distinct ends, and this function, this extension, must satisfy the following Vasilyev's four-term relations, which look like follows. We have a chord diagram. We have two chords with neighboring ends, and starting with these two chords, we construct three more chord diagrams such that they can have additional set of chords which is the same for all chords having ends on dot arcs of the diagram, while the distinguished two chords acquire these four possible positions. To each finite type not invariant, one associates a function on chord diagrams, and the famous Kontsevich theorem states that the converse essentially is also true, so that each weight system taking values in an algebra over a field of characteristic 0 arises from some finite type not invariant. So that there is more or less one-to-one correspondence between weight systems and finite type not invariance. It is, of course, interesting to construct weight systems, to construct in some way functions on chord diagrams that satisfy four-term relations. And there are two main sources of such constructions. One source is graph invariance. I'll explain how it works, but I will speak mostly on the other class of constructions, namely constructing weight systems from Lie algebras. The main difference between these two constructions is that those weight systems that come from from graph invariance are usually can be easily computed, but they are not powerful, while those coming from Lie algebras are extremely powerful, but it is very hard to compute them generally. How the construction from Lie algebras proceeds? We start with a finite dimensional Lie algebra G, endowed with a non-degenerate invariant scalar product. The invariance meaning that for any triple of vectors x, y, and z, the scalar product of the commutator of x and y with z is the same as the scalar product of x with the commutator of y and z. And then we proceed as follows. Pick an arbitrary orthonormal basis x1, xd in the Lie algebra, then cut the circle at some point, which can be arbitrary, and develop the outer circle into the straight line. After this, what we obtain is an arc diagram. Chords become the arcs, and we put one and the same element of the basis at both ends of the arc. As a result, what we obtain is a word, a product of the elements of the basis, which is an element of the universal enveloping algebra. And then we sum these elements over all possible ways to mark the arcs of the diagram with the elements of the basis. An easy theorem due to Dror Barnatan and in a different form to Maxim Kontsevich states that first, the result of such summation is independent on the choice of both the basis, the orthonormal basis we have chosen, and the cut point, so that we obtain a well-defined element of the universal enveloping algebra of G, which in fact belongs to the center of this universal enveloping algebra, and this mapping taking a co-diagram to the center of the universal enveloping algebra satisfies the four-term relations, so that what we obtain is indeed a weight system. However, whatever easy is the definition, it is a very hard task to compute the result, because we are obliged to make computations in a non-commutative algebra, in a highly non-commutative algebra, which is the universal enveloping algebra of the Lie algebra. And in spite of the fact that the result belongs to the center of this universal enveloping algebra, which is a commutative algebra, all the intermediate computations are to be made in a non-commutative situation, which makes them extremely complicated. With a single exception, for the simplest Lie algebra SL2, there is a recurrence relation due to Sergei Chmutov and Alexander Vashchenko, which allows one to compute the values of the SL2 weight system directly, not using it, not making intermediate computations in the universal enveloping algebra. That is how this recurrence relation looks like, how it works. It happens that in any sufficiently complicated chord diagram, there is a triple of chords either in the position shown in the first line or in the position shown here. Once again, on this solid arc, there are no intermediate arc chord ends between the ends of these two chords as well, here and here as well. And in this case, one can replace a chord diagram, but by 5 more simple chord diagrams, the first 3 of which have fewer intersections of the chords, while the last 2 have fewer chords. So that this is indeed a recursion relation which allows one to replace a chord diagram with simpler chord diagrams. And we may proceed recursively computing the results of this, computing the value of this SL2 weight system. However, even this algorithm is rather complicated because we replace a chord diagram by 5 other diagrams at each step, so that we have an exponentially complicated algorithm which does not allow us to proceed much further. And until recently, the explicit values of the SL2 weight system have been known only for fairly simple chord diagrams and families of chord diagrams. In 2007, Sergei Chmutov and me, we proved that the value of the SL2 weight system on a chord diagram depends on the intersection graph of the chord diagram only, not on the diagram itself. The intersection graph is a simple graph whose vertices are in one-to-one correspondence with the chords in the diagram, and two vertices are connected by an edge if and only if the corresponding chords intersect one another, so that one may speak about the value of the SL2 weight system on graphs that are intersection graphs of the chord diagrams rather than on the chord diagrams itself. And I will proceed like that. In order to explain the following theorem due to Polina Zakorka, I have to address another invariant of graphs, which is in fact a weight system. If you consider it as the invariant of intersection graphs of chord diagrams, and this invariant is a very well-known chromatic polynomial of a graph. The chromatic polynomial counts the number of proper colorings of the vertices of a graph into a given number zero of colors. And it is easy to see that if our graph is the complete graph on n vertices, the complete graph on n vertices, which is a graph for which any two vertices are connected by an edge, then the corresponding chromatic polynomial looks like C times C minus 1 times C up to C minus n plus 1, which is the following factorial of C, of the number of colors. We are able to color the first vertex in arbitrary C colors, then the second vertex. For the second vertex, we can choose C minus 1 colors that are not coinciding with the first one, and so on and so forth. And there is a very nice formula for the generating function for these following factorials, for the generating function for chromatic polynomials for the complete graphs, which represents them as the Jacobi continued fraction. 1 over 1 minus ct plus ct squared over 1 minus c minus 2t plus 2 times c minus 2t squared, and so on. So that the case rho in this continued fraction looks like 1 minus c minus 2 times k minus 1t plus kc minus k times k minus 1 over 2t squared. It happens that for the values of the SL2 weight system on the complete graphs, on the chord diagrams in which all the chords intersect one another, a similar continued fraction for the generating function takes place. You see, this generating function also starts with the following factorials, but already the fourth term is different. It is c times c cubed minus 6 c squared plus 13c minus 7. And the formula for continued fraction, also very similar, is different. Instead of 2k minus 1 in the linear term, we obtain k times k minus 1 here. A linear polynomial is replaced by the square polynomial, by the quadratic polynomial in k. And here, instead kc minus k times k minus 1 over 2 t squared, we have k squared c minus k squared times k squared minus 1 over 4. This conjecture, I came to this conjecture around 2014, but was totally unable to prove it until Paulina found a nice way to argue. And in addition to proving this formula, she developed several instruments for treating SL2 weight system on so-called shares, which allowed Maxim Kazaryan and Polina Zinova to compute explicitly generating functions for the values of the SL2 weight system on complete bipartite graphs, which can be written in the form of a recurrence formula for corresponding generating functions, where the coefficient SIM here also are given explicitly, so that during the last couple of years we have got numerous highly non-trivial families of code diagrams for which we know the values of the SL2 weight system explicitly. And at the moment, the last result in this direction is the SL2 duality, which generalizes the results for the complete bipartite graphs in the following form. A complete bipartite graph can be considered as a join of two discrete graphs on M and N vertices respectively, and instead of these graphs, we can consider families of joins G, N, for an arbitrary graph G and a discrete graph on N vertices. Zakorka and Zinova and Kazaryan proved that the generating function for the values of SL2 weight system on these families of joins have a similar form. They are linear combinations of rational functions whose denominators are 1 minus c minus m times m plus 1 over 2 times t, with the polynomials with the, whose numerators are polynomials in C, for some sequence of polynomials depending on the number, depending on the given graph G. And Polina Zakorka and Polina Zinova proved a duality formula for these polynomials. It happens that if we know these polynomials PMG of C for some graph G, then we also know them for the dual graph. The dual graph, the complement graph of G, G bar, is the result of, we take a graph G, we preserve the set of its vertices, and we switch all the edges in the graph. The set of edges in G bar is complement is complementary to the set of edges of G. And then the polynomials PMG for G bar remain the same, but half of them changes the sign, so that this is indeed a duality. The paper will appear on the archive the day after tomorrow, I hope. Will finally appear. But what can be said about more complicated Lie algebras, about more general Lie algebras? SL2 is just a single SL2 is just a single example which corresponds to a very powerful and influential not polynomial, which is Jones, which is colored Jones polynomial, but there are much more powerful Lie algebras. And for the series GLN, Maxim Kazaryan suggested an idea which proved to be extremely fruitful. The idea is to construct a recurrence by extending the weight system from code diagrams to permutations of more general form. In fact, Maxim Karev, who participated the previous part of the conference, explained to me that this construction of extending weight systems to permutations was contained implicitly in his paper with Sergei Duzhin. I do not remember, maybe around 2007, but there was no recurrence and no idea how any reasonable computations could be done. In order to explain this construction, I will modify slightly the construction of the weight system from a Lie algebra, and instead of an orthonormal basis, I'll consider an arbitrary basis in the Lie algebra. And in this case, what we write on the left end of the corresponding arc, we write an element of the basis, while on the right end of the same arc, we write the dual element of the basis, the dual with respect to the chosen non-degenerate scalar form, and it happens that the result will be, in fact, the very same element of the Lie algebra, whatever basis we have chosen. In this construction, it is easy to see how the GLN weight system can be extended to permutations. If you take for the basis in GLN, we choose the standard basis of matrix units, EIJ, so that EIJ corresponds to the n times n matrix having 1 on the intersection of the ith row and j's column, and all whose other elements are 0. And the symmetric matrix EJI is the dual to the matrix EIJ with respect to the standard to the standard scalar product given by the trace of the product of two matrices. And now the key construction. If you take an arbitrary permutation of arbitrary number of elements, m, then we are able to associate to this permutation an element in the universal enveloping algebra of GLN, which is the sum of the products of matrix elements. The products are understood as the products in the universal enveloping algebra rather than matrix products. We take I1, I sigma of 1, I2, I sigma of 2, and so on and so forth. And then we sum these products of matrix units over all possible ways to number the permitted elements with indices from 1 to n. Now, an easy statement, maybe not that easy, but it is also true that the result of applying this mapping to an arbitrary permutation sigma provides us with the element of the center of the universal enveloping algebra of GLN. And in order to explain the recursion, I will need the notion of a simple notion of a graph of a permutation. We simply, in order to describe a permutation, we just put all the permuted elements along the straight line, and in blue, we show the arrows showing where each element is taken by the permutation. 1 is taken to n plus 1, n plus 1 is taken to 1 in this example. This is an example of a permutation in which all the cycles are of length 2, so that this is an involution without fixed points. And in this way, chord diagrams can be described. Chord diagrams or arc diagrams, they describe, they can be considered as permutations which are involutions without fixed points. And it is easy to see that for the Lie algebra GLN, this construction of weight system GLN on permutations exactly coincides with the construction, with the original construction of the weight system on chord diagrams, so that this is indeed an extension. This is indeed an extension of the GLN weight system to arbitrary permutations, not necessarily chord diagrams. For the standard cycle, 1 goes to 2, 2 goes to 3, and so on. M goes back to 1. The value of the corresponding weight system, GLN, we define that this is the M-Casimir element of the center of the universal enveloping algebra. And the well-known classical theorem states that for a given n, the center of the universal enveloping algebra GLN is naturally identified with the ring of polynomials in the variable C1 up to Cn. So that our weight system on permutations takes values in the ring, in the polynomial ring of polynomials in n variables. And now we are coming to the recurrence. In this recurrence, we represent any permutation as by means of its directed graph, the directed graph of the permutation. And if we take two arbitrary neighboring permuted elements, L and L plus 1, then we are able to exchange them, to exchange this element, to switch them for the price of the difference of two permutations of the values of the GLN weight system on two permutations of smaller number of elements. Here on the left we have each of the two permutations permutes m elements, one, while on the right each of the two permutations permute m-1 elements. And this is indeed a recurrence relation which allows one to replace a single permutation of n elements with three permutations, with three simpler permutations. And this is the first, using it we are able to to construct effective algorithm of computing the value of the GLN weight system on permutations. Here is a special case of this construction when our permutation takes an element k plus 1 to the element k, then we are able to undo this intersection, and here will appear the element C1, and here will appear n, which is the rank of the Lie algebra GLN. As an example of this computation, we are able to compute the value of the GLN weight system on the cycle of length 3, which is inverse to the standard one. And here the cycle is 1, 3, 2. By replacing the elements 2 and 3, we get the cycle 1, 2, 3. And what's happened on the right, we already know, so that the value of the GLN weight system on the inverse cycle is C3 plus C1 squared minus n times C2. Well, an immediate and very important corollary of this construction, of this recurrence relation, is the following one. It happens that we are able to glue all the GLN weight systems together in a single universal GL weight system, which takes place in the ring of polynomials in infinitely many variables, the first of which is n, which is nothing but C0, and all the other Casimirs of all possible with all possible indices. And if you have this universal enveloping, universal GL weight system, then we are able to specialize it for any given value of n. In order to do that, we preserve C1, C2, Cn, substitute n equal to the specific number, and use a standard expression, a standard way to express the elements Cn plus 1, Cn plus 2, and so on in terms of the first n Casimirs. Now, this was exactly, this is the argument, and the way of reasoning is very similar to what Andrei Okounkov explained for going to infinity in the way in characteristic classes. So now we have a very explicit construction for GL weight, for the universal GL weight system for code diagrams and more generally for permutations. And we are able, we have an algorithm to compute it, but and then what we get, for example, for the code diagram consisting of 5 intersecting codes, we obtain a huge polynomial in variables n, C1, C2, and so on. And it is very interesting to understand what kind of information is encoded in this polynomial. The polynomial is huge, and from the first glance, it is not clear how we can use it and obtain, how we can use it and obtain some reasonable information. While you were leaving, I was mentioning you. How can I? What kind of information does this polynomial contain? One way to make this question more precise is to ask which graph invariants can be extracted from these polynomials. And there is at the moment we have already a number of rather non-trivial statements. It is easy to show, for example, that there is no substitution of the values n and the values of Casimir's that makes this polynomial into the chromatic polynomial of the intersection graph. However, it happens that if we make the substitution ck equal to x to the power nk minus 1 for all possible values of k, then we obtain a polynomial in 2 variables, which are now n and x. And if we take the leading term in n of this polynomial, then this leading term on a code diagram becomes, it is a polynomial in x, which is exactly the chromatic polynomial of the corresponding intersection graph, which is a rather unexpected situation. Moreover, if we replace our code diagram with an arbitrary positive permutation, then the assertion of the theorem remains true. By a positive permutation, I mean a permutation in which all the elements in each cycle go in one direction. But the last one, from the last one, we return back forwards. And there is a number of other theorems related to this chromatic substitution. Other graph invariants, a number of other graph invariants also can be extracted from this polynomial. Here I mention only that there is a substitution which provides what is called interlaced polynomial of a graph. This result is due to Nadia Kodanyova and myself. I'm not given the definition of the interlaced polynomial, but nowadays it is a rather interesting and well-investigated polynomial. What's interesting about that? So we have a substitution which provides for code diagrams the interlaced polynomial of its intersection, the intersection graphs. But the substitution is well defined for arbitrary permutations as well, so that we obtain some polynomial invariant of permutations. What can be done with this polynomial? What is the interlaced polynomial of permutations? What are its properties, and what is its meaning? In addition to weight systems constructed from Lie algebras, there is a similar construction for weight systems from Lie superalgebras endowed with non-degenerate invariant scalar product. And Georgian elaborated as well the extension of the corresponding weight system for the Lie superalgebra GLMN to permutations, and he has shown that this extended weight system can be extracted from the weight system for the Lie algebra GLN if you set n capital equal to the difference of m and n in the defining for the ranks of the weight system of the Lie superalgebra weight system. And for other classical series and of Lie algebras and Lie superalgebras, the result is also obtained by Maxim Kazaryan and Jackie Young, and I still hope that the paper will appear in the nearest future, although I hope for this for already half a year or so. What is the relationship of these pictures to what Igor Krechever has been done, and how these objects are related to his field of interest? During the last decades, one of the most close domain of research to Igor was the theory of real normalized differentials on algebraic curves. A meromorphic differential on a curve is real normalized, provided all its periods are real, so that the integral of this differential over any closed curve on the surface is real. And Igor hoped that real normalized differentials can be useful, and in a number of important examples, he has shown that they can be useful in understanding the geometry of moduli spaces of algebraic curves. For the case of real normalized differentials with a single pole of order 2, the relationship can be established as follows. Any such differential determines a line field on the curve x. This is the field of lines looking in the direction in which the integral of the one form omega increases. The imaginary part of the integral increases, the real part is preserved. This line field has several separatrices, such that if we cut our surface over the separatrices, then what is left is just a cell, and there is a natural mapping from this cell to the complex line, the image of which is a complex line cut along several half lines. These half lines are split into pairs, starting at one and the same level, so that in fact these half lines determine an arc diagram. We are able to, if we connect the corresponding lines with an arc, what we obtain is an arc diagram. And the space of meromorphic differentials, is stratified according to this arc diagram. This arc diagrams number strata of the highest dimension in this stratification. The second Vassiliev move, which appears in the four-term relation I have shown in one of my first slides, the second Vassiliev move is exactly what happens with this strata as we cross the walls in this stratification. So that this stratification is very closely related to arc diagrams, but not only to arc diagrams, but also to more general permutations, since as the separatrices collide, we obtain strata of higher codimension in our stratification in the moduli space of meromorphic real normalized differentials. These strata of higher codimension are enumerated by permutations of more general form than chord or arc diagrams. Let me now discuss some. There is a huge number of problems. Each time we discover some new direction, new approach to old problems, a huge number of new problems emerges immediately. For example, this problem is an old one, and this problem is the one which initiated our study of SL2 weight system. As I have mentioned, the SL2 weight system depends on the intersection graph of a chord diagram rather than on the diagram itself. A natural question is whether the SL2 weight system can be extended to arbitrary graph, not necessarily those graphs that are intersection graphs of chord diagrams, and this extension should satisfy the four-term relation drawn on my T-shirt, so that it would be very interesting to know whether such an extension exists, and I hope that the results obtained in the form of explicit computations can help a lot to achieve this goal. A partial answer given by Fomichev and Karev, who, as I have mentioned, took part in the first part of this conference, says that this is possible for the value of the SL2 weight system at the C equal to 3/4. They use a different normalization. In the normalization I was spoken about, it is 3/4. But we don't know about other values of C, most of the values. The paper by Fomichev and Karev appeared on arXiv 3 days ago or so. Now, I've told you that the chromatic polynomial appears as the leading term of the universal GL weight system under the substitution Ck equal to x to the n to the power k minus 1. But there are other terms as well. For example, what about the second term of this asymptotics? What combinatorial meaning does it have, and what is how we can interpret this this term and the other terms as well? And what is the combinatorial meaning of the chromatic polynomial, of the chromatic substitution for arbitrary permutations, not necessarily chord diagrams? Interlaced polynomial also leads to similar questions. Now, chord diagrams can be treated as orientable maps, combinatorial maps with a single vertex, while permutations are orientable hypermaps with a single vertex. What about more complicated maps and hypermaps, where we do have arbitrarily many vertices, not just one? And in the stratification of the space of meromorphic differentials, I have talked about chord diagrams, and permutations come not as combinatorial objects, but as metrized objects. Each arc here has a length, which is the integral of our differential form between the corresponding points. One can write down 4-term relations for this continuous situation. What is this meaning? What is the meaning of these 4-term relations, and how we can construct invariants, more general invariants in this continuous case? And there is a huge number of other problems and questions, but I have no time to discuss them right now. Let me stop here.
Thank you very much. Question, please.
I have a couple of questions. So first of all, maybe there are framed versions of all of that. I mean that we can have framed chord diagrams, and it seems logically that super Lie algebra stuff should be variable if we have 0 and 1.
Yeah, I totally agree with you.
And the second question is, maybe if we consider something which is not realizable by chord diagrams, but by permutations, maybe it can be related to unit Ravel and Feynman diagrams, which were impolitely called by Barnatan in his initial paper on the Vassiliev knot invariants.
In this case, I'm not quite sure because these Chinese characters, how they were called by Barnatan, they are used to express code diagrams. There are some linear combinations of code diagrams. For permutations, this is not true. They cannot be expressed as code diagrams.
Yes, but maybe if we consider such a Chinese diagram, maybe there is an intersection which is realized not by a chord diagram, but something like that.
Maybe.
Okay, thank you.
Thank you. More question? Thanks again.
There is potentially a third way of getting weight systems. Maybe actually this Krzyzewski construction is actually in that direction. I think any holomorphic symplectic manifold should give you a weight system from Rosansky-Witten invariance. And so, if I have a curve, Hitchin system associated to this curve for any Lie group would give you a holomorphic symplectic manifold. So if you do it for SL2, this Hitchin system will be fibered over the space of quadratic differentials. You can allow poles. The fibers are Jacobian, so maybe you don't see them in this.
Yeah, you're right, but I never made computations with the symplectic manifolds, therefore I'm unable to interpret this.
Thank you, sir.
No.
Okay, let's continue. Our next speaker is Senya Schlossman, pedestal polynomial matrices with polynomial eigenvalues. Please.
Thank you. So I see that this talk has several things in common with just the previous one. So I also want to say something about what that has to do with Igor Krichyver. So unfortunately, not that much, but he was very happy with the list of authors because at the moment that the paper was written, Will Savin was in Columbia, and I was still in Skoltech, and he was saying that he is a good addition to our team of authors, and by now he moved to Princeton, right? I mean, Will Savin. Yes. So so I will also I will have some operators in my talk, but those are not commuting operators. So this is not. Igor has not much to do with well, he is not famous for that. But being the oldest participant in this room, I believe, I decided that I say just few words about Igor because it turns out that I know him more than half a century. Half a century. That's strange to think about, even such numbers. So this is me and him in our first boat trip, which was during our students' year, and this is we are sitting at military training in 1971. So this is him. This is Igor. This is Borya Dubrovin, and this is me here. And we had many boat trips with him. This is some intermediate one. He's with Natasha, his wife. That next one is our last trip, which is about 5 years ago. We are doing some topology here, as you see, trying to figure out what to do with this thing here. And this is the last picture is Serge Novikov with his friends and colleagues. As you see here is Igor standing here. This is Serge Novikov. This is our chairman, right? And this is again Vori Dubrovin. This is Viktor Buchstaber and others. Okay, so Serge Novikov also passed away this month, as some of you know. So okay, this is now I pass to the topic of my talk. So this is that was just what all that had to do with Igor Krichever. So this talk is mainly about combinatorics of diagrams, of three-dimensional diagrams, plane partitions, and generating functions. So I will go slowly and with details, so you can ask questions if something will not be clear. So I start with reminding you what Young diagram is. You just take the number k and you write it down as a sum of non-increasing integers. So the pi of 1 is the biggest one, and then the last one might be several of the last one might be 0. So this is a partition of the number of k, and schematically it can be drawn in such a way. So it is such a staircase, and so we have here we have totally 21 boxes in that partition. And then what one likes to know is the generating function, as we heard in the last talk. So this is you want to know how many partitions of total area k is there, and then you write down the generating function for that sequence. It turns out that this generating function is given by this product of 1 over 1 minus t to the L. L runs from 1 to n. And this is easy to see, in fact. So if you indeed expand this product, this is the product of those series, and then how you establish this one-to-one correspondence between the terms here and the diagrams. For example, in this one, see you have 2 rows of length 1. So you go to that product, and then you take from that sum the second term, t to the 2. That means you have 2 rows of length 1. Then you have no rows of the length 2. So from the second term you take just 1 here. Then you go back and you see how many lines of length 3 you have. Again, you have 2. So you go and you take from that product. Oops, go wrong way. From that product, you take the term t6, t to the 6, and this is the one-to-one correspondence between partitions and terms of that product. Okay, so this is all well known. So this is a reminder, and then you want to talk about plane partitions or two-dimensional analogs of those pictures. For example, you take a rectangle 2 by 3 here, and then you put boxes like that. So those are the boxes of the same height as before. So you arrange them in such a way that the heights decrease to the right and to the front. And again, you want to count how many of those are there. And this is again a famous question, and it has a famous answer. This is given by the McMahon formula. And so this is again a product over this rectangle, NYM. And here we have 1 over 1 minus t to the power L plus S minus 1. And this power is just, is known as the Hooke length of the cell LS. So you draw this rectangle, you put a point with coordinates L and S, and the area of that hook is what is appearing in this formula here. Good, and evidently there is a natural map from the set of all those plane diagrams to the usual Young diagrams. You just list all the columns of your skyscraper in decreasing order, and then you have a map from this set of all plane partitions to the set of Young diagrams with n times m entries. And okay, would be nice to have sort of an inverse map to that, but unfortunately the preimages of the various diagrams have different number of the number of preimages is different depending on the diagram, so it might be tricky, but now I want to explain in which sense one can do something like that. Namely, what one should do is to
Space is closely related to hexagonal tiles. So when we look at a picture when some cubes are put together, it's related to some two-dimensional picture. And whenever we have tilings of squares or cubes of higher dimensions, it should be related to two n-gons and the ways of gluing and zonotopes and so on. So I'm asking whether there are some group actions and some topology on the Young diagrams, Young tableau, and their higher dimensions.
I have to say that I totally agree with what you said initially, and I will not comment on the second half because that would take me for too long. So I want to discuss still the relation between those two sets, and the relation. To explain the relation, I have to introduce those pedestals, which is a main object of my talk today, the main character of this story. So to explain what that is, let us take this rectangle n times n, and let us fix some linear order on it, which, for example, the one which on the top, that is one possible option. This is the other possible option, and then what we do. So imagine we have two different linear orders on this rectangle, and then we want to consider. Then we define what is a disagreement between those two linear orders. So we call a node a disagreement node if the order, the two nodes appearing under P and under Q, those are reversed orders. Then we call this a disagreement node. And for example, on that picture, we have one single disagreement node, this one, because see, we proceed. So this is our P, and that is our Q, and we proceed over Q, and then we increase this way, we also increase that way. Here we go this way again. This is consistent with that order till we get here. Here we go down, and there we go in the opposite way. So we have one conflict here, and then this is the only vertex that we have the conflict, so we mark it, and then we define what is the pedestal of this second order, which is down there, with respect to the first one. In the following way, there is this formula here, but let me just tell you what that is. So there is one disagreement here, this side, so we put a 1 here, and then on all further vertices we also put one till we get to a second descent, and then we're starting from there. We put 2 and 2 and 2 till the third place. Okay, and this is again is sort of a plane partition. So all those plane partitions that you get this way, we denote by Q with the index P and Q. Those are two orders that we use to define it. Okay, and then the fact is that there is a bijection between the set of all plane partitions, the set P sub Mn, and a direct product of all Young tableaus of length n times m, and the set of all those pedestals E with the subscript P. And this one-to-one correspondence is explained here. So what one should do is the following. So imagine I want to define it from right to left. So let me take a partition pi, and let me take a pedestal q. Then the corresponding plane partition, which is on the left-hand side, which I want to build from this Young diagram and this pedestal, is the following. This pedestal has some running order here. This is q. So you take your partition P sub k, and you put it along that order. So you have an order, and then you put the members of this partition along that path. This Young diagram you put along that path, and then you also have to add the pedestal of this. Say it again. So P is, in this formula, P is fixed. P is fixed. Then you define the set all pedestals of P, and then you take all diagrams. And to every diagram and every pedestal, you correspond a partition. So you take your partition, you put it along the order of Q. Q gives you an order on your rectangle. So you put those y's, the terms of this one, and you add this other plane partition. Sum of two plane partition is again a plane partition. So this is a new partition. The claim is that this is a one-to-one correspondence between the two. Okay, so, and in particular, so if we now consider the generating function of the pedestals, then this bijection that I just mentioned shows that there is a formula, another formula for the generating function of plane partitions, which is just the generating function of Young diagrams times the generating function or generating polynomial of all pedestals. So just this is another way of writing down the generating function of plane partitions. And what is nice about that formula is that you can do this not on just plane partitions, but on every partially ordered set. For example, you can talk about space partitions, and you get a formula for four-dimensional Young diagrams. And McMahon also wrote down such a formula, but unfortunately his formula is very nice, but nobody knows what it counts. But in this way, you can write down those formulas in any dimension. So in particular, if we compare those two formulas, the McMahon formula and the one I told you, we see that there is in this fraction, actually, there is fine cancellation. So this ratio actually turns out to be a polynomial, though it is not straightforwardly evident. Okay, so those are the pedestals. And now what one can do is the following. So let's take So this is not a rectangle, but you can supplement it with number 6. Then those are all 6 possible orders on the 2 by 3 rectangle, and you then you can write down then you can form a matrix. This matrix is indexed by pairs of linear orders on your set. So there is 5 by 5 matrix. Good, and then you try to compute the eigenvalues of that matrix. And the miracle is that those eigenvalues are those polynomials here. So looks like a miracle that cries for explanation. We tried several of those matrices, several cases, and all the time the eigenvalues are given by this by some polynomials. So we wanted to understand why that is. So actually, it is 5 by 5 matrix, but the sum of along every row is the same. So that's another eigenvalue. This one is a polynomial is just the sum of those monomials. So that is the case. So all 5 eigenvalues are polynomials like that. And so the driving question for us was to understand whether this is always true, and if yes, then why that is the case. And indeed, this is the case, and even more general fact is known. So instead, before what we did to every pedestal, this QPQ, to this guy, we were corresponding just its volume, Q to the volume of that pedestal. But actually, you can associate to every pedestal a monomial of several variables. So this is how many floors that pedestal has of height 0. This is how many L1. It has L1 minus 1 cells with height 0, L2 minus L1 of height 1, and so on. And so you associate to every pedestal a whole monomial. And this Q to the power, Q, in that case, T to the power is just, if you put x1 to be 1, x2 to be t squared, then you get the previous formula. And again, it turns out that the sum of all those monomials over rows of such a matrix is the same. So it's, in a sense, it's a stochastic matrix. And then, in fact, one can do the same thing not only for plane partitions, but one can do this just for any partially ordered set, for every poset. And so one can consider again this matrix, which is this pedestal matrix. And the main result of this talk, which is obtained together with Richard Kenyon, Maxim Kontsevich, Oleg Agiyevetsky, Kozmin Pohuata, Will Savin, and myself, is that this matrix, all the eigenvalues of that matrix are again polynomials with the integer coefficients. So this is surprising, right? Yeah. So this we were mesmerized by this for some years, but finally we have a proof of that fact. And so let me give you another example. Let us consider this partially ordered set with 6 elements. So it's just a Young diagram written there, drawn there. That one has 16 orders. So the matrix then is 16 by 16. So those monomials are monomials which would appear in that matrix. So for brevity, they are denoted by A1 to A10. So this is the matrix, 16 by 16. And then you compute the eigenvalues. And again, those are the eigenvalues here. So those are polynomials in those x variables. And the last line is just the sum of all, sum along the row of those a's, and others are sum with alternating coefficients. And this index here, that means that this value appears 3 times. Okay, so this is the theorem, and I want to explain the proof of it. And the proof is, well, there appears some objects which we were not initially counting on seeing. So the result, what we would show is that the matrix MX, this matrix of pedestal matrix, can be written as a linear combination of some other operators, MFs, with integer coefficients. And though they are not commuting, those MFs are not commuting, but anyway, one can do conjugation of all, a simultaneous conjugation of all those MFs in such a way that the resulting matrix would be upper triangular with integer entries on the diagonal. So this is, and that would imply our statement. So there are many, okay. So that's how it goes. So let me try to explain what those MFs are. To explain that, I first tell you what is a filter of a partially ordered set. So if X is a partially ordered set, then you consider, oops. Then we consider a surjective map from X to segment of integers from 1 to k, which k is less than or equal to n. And then the only condition is that it respects the partial order. If we have a filter and it has B1 occupants on the first floor, B2 occupants on the second floor, and so on, then we denote in this way all the filters which have this restriction that the population on the level I of that filter has Bi occupants. Okay, and then if we have a filter F on X and the linear order on X, then we can build a new linear order, Q, which would depend on P and on F. And the construction is the following. If we take some floor of the filter F, it is all the values, all the points of X where F is taking some constant value, then we just put on that floor, we just keep this partial order P there. And if the elements alpha AI and alpha Ji in different floors, then we put the order, the same order as they are ordered according to that filter, F. So once we have a linear order P and the filter F, then we define a new linear order Q of F and P. And then we define this matrix, this MF, the matrices that we would enter the proof, and it is a definition. So the matrix MF, the matrix element, the matrix is indexed by 2 linear orders, and so the entry is 1 if the order Q is obtained from order P by action of that filter F, and it is 0 otherwise. Okay, and so those it turns out that those matrices, they form actually a semigroup. If we multiply them, you get again you have also a matrix which is again it corresponds to some other filter. So there is some structure on those filters, but it is easier to explain this geometrically. So this filter semigroup is better defined to be a phase semigroup. So I define some other semigroup, and then I will tell you that those are the same. So what is this phase semigroup? So we have n is our number of elements in the X. So what one should do is the following. One takes n-dimensional subspace, Rn, and one define what is called braid arrangement AN of hyperplanes in the space Rn by just considering all the hyperplanes Hij, which are which are defined like that, where the ith coordinate is coinciding with j's coordinate. And then if you take away the union of all those planes, you get a collection of cones, open cones, and each such component is called a chamber. And then if you take several chambers and the union is convex, then what you get would be, it is called a cone. So let D of n would be the set of all different possible cones defined by this braid arrangement of hyperplanes. Okay, now to every partially ordered set of n elements, one can define what the corresponding cone of that. Namely, you take all the half space kij, which correspond to the relation I is less than or equal to j. You take those half space, and you then take all the intersection of all those half spaces, and then you get a cone because it's an intersection of half spaces. So to every partial order, you correspond a cone, and what turns out is that this correspondence is a one-to-one correspondence between all structures of all options of putting partial order on X and all cones that you can see in this hyperplane arrangement. And then when we understood that, we was a little bit puzzled, so we decided to check it. So we took the case when you have four different elements, like you see on my T-shirt. There are four individuals, so those four are different. And then you want to know how many partial orders you can put between them. So this is the intersection of this hyperplane arrangement A4. You should project it into R3, and then you intersect what you get with the unit sphere, and then you get such a nice picture. It almost looks like a Platonic body, except that those rectangles are not right rectangles. They have two angles are 60 degrees and one angle is 90 degrees. So there are 24 triangles which are partitioning the sphere, and then you count how many convex sets you can get from those. So there are many ways you can do them. You can take the whole sphere, the hemisphere, a piece of it between two great circles, which are moons, and so on and so forth. You add all them, and then you find out the number 219. There are 219 different convex sets, and this is the same as the number of partial orders that you can put on four different individuals, distinguished individuals, as you can find in this list of sequences. You can find this number there. So after that, we were sure that this is a correct statement. And now there is, as I told you, there is a structure of semigroup on those faces of this on this set of on that structure of hyperplanes and all faces of lower order. So there is this definition here. What is this product? But let me just explain it on the picture. Okay, maybe I use this other blackboard. So so this is analog of that picture for it in dimension 3. So we have here 6 chambers, 6 faces of codimension 1, and 1 face of codimension 2. So the product is defined as follows. If I want to multiply this chamber with this face, for example, I choose a point here, I choose a point there, so I multiply this chamber, say F1, by this other chamber F2. So then F2 acting of F1 is defined as follows. You take a point here, you connect it with a segment here, and then you make a little bit a step back, so you get here. That belongs to some chamber. So this is F3. This is the one which corresponds to that point. That point belongs to that. This is the smallest chamber that contains that point. So this is your definition. So this is this phase product. This is the structure of of this. This is a definition of the product, and that product has some properties. And for example, if F double prime is a chamber, then F double prime F prime equals to F prime. And again, if F prime is a chamber, then F prime F double prime is also a chamber. So the phases are acting on chambers here. And
Excuse me, I'm pretty sure that this should give rise to actions of plate groups on young tableau of 5 dimensions. So when we switch from one situation to another situation, when we do some plate arrangement,
it seems that this is not a question, I believe, right? So maybe you'll then say it later on. Thank you. Okay, so this product is associative. So this is indeed a semigroup, and it has certain properties. So F squared is F. So all those are projectors, and FGF equals to FG. And because of that, this semigroup is called left regular band. This is a name we learned after we found that. Okay, and then on that slide it is explained that the filters and the phases are just the same thing. You might just believe me, and then let us go further on. And this is, and then one can understand what does it mean to have two filters, to multiply them. Well, you just read it out from the definition of the product of phases. Good, and then finally this object appears. This matrix M sub F is the following. You take a filter F, and you take a linear order, which is also a filter, and then you define the matrix MF with entries which are indexed by pairs of linear orders. The matrix element PQ is equal to 1 if the order Q is obtained from the order P by action of the filter F, and it is 0 otherwise. So those operators are important for the proof of the theorem I promised. And the remark is, again, as I told you, those are not commuting operators. And the fact of life is the following, that if we take our pedestal matrix MX, and this is just, it is written as a sum of monomials times a matrix with entries 0s and 1s, and then there comes a formula which is just exclusion inclusion formula here, and I don't want to explain this because, but one stares for it for a few minutes, and one see that indeed this is true decomposition of the objects that we are interested in over those matrices MFs for different Fs. So you see here there are different subsets of filters. So this is just exclusion inclusion formula, and I will not say much about it. But here it is written why it is true. So if you want to read this and then think about it, then probably the slides would be available. That's why this inclusion exclusion formula holds. Very good. So then from now on there is a straight way to do the conjugation that I promised, namely, so we have our matrices MFs they are of the size of how many linear orders on X are there. Now let us throw away all the linear, or let us take X to be totally unordered set. So it has n factorial elements. If we don't have any partial order, then it has much more linear orders than initially it was. So and so now matrix M of X is a submatrix of M f X bar when we abandon all the orders. You look on it for a while, and then you see that this M f X is a block of the matrix M f X bar, a square block of it. So if the bigger matrix has all eigenvalues integers, whatever you want, then the smaller one also has the same. So you don't actually need the order on X. Without order, it is. So we prove more. We prove that the bigger matrix has all eigenvalues which are integers. And then we go to still bigger matrix, which is what you do. Before we were talking about, so now we put a very, very mild order. We take all the edges and we order every edge independently of each other. This is called tournament. So on every edge independently of each other, we put a relation, bigger or equal. Very good. This is still bigger matrix. And again, the matrix we are interested in is a block of that bigger matrix. So why don't we study if this even bigger matrix? And again, filters are also acting on those tournaments in the same manner as it was acting on linear orders. So we still have those matrices there as well. And then, so we have to study those matrices M sub F. F is a filter, and T is all possible tournaments on the set of n elements. Very good, but then the final remark is that this biggest matrix is actually a tensor product of 2 by 2 matrices, because the tournaments are so defined that on every edge you do it independently. So the matrix we're interested in is just a tensor product of 2 by 2 matrices, and therefore it's enough to check what we are going to prove just in the case n equals 2. So just one edge, and you consider all possible tournaments and filters there. So there are just 3 matrices here, which you see. And then you just check that each of those 3 can be conjugated by this matrix U, which is 1 over square root of 2, 1, 1, 1 minus 1. And then you do the 3 conjugations, and you see that all the diagonal elements are integers. That's the end of the proof. So you know the story that somebody came to a circus selling them the trick that a crocodile is playing piano and the monkey is singing. And everyone was very mesmerized by this, and they were asking, how you do this? And finally, the answer he gave after some time was that, you know what, of course this is a lie. So monkey only opens its mouth. The crocodile is playing and singing. So this is how that proof works. So that's it. Thank you for your attention.
Thank you very much. Question, please. Question, comments? Yes, please.
Can you repeat how did you use discrete Fourier transform?
I cannot hear you even with the mic. Huh? Forget it. Just take this matrix. But they no, they are not. They are not.
Okay. Thank you very much. Thank you very much.
Thank you for your attention.